The following message is best viewed on an oscilloscope.
Okay, I would like to welcome everybody to the formal theory development session. So it's a pleasure to host this meeting at unusual times. My name is Jaroslav Trnka. I'm from UC Davis, and I will be the session chair today. We will have a set of very interesting talks. And I would like to just remind some rules. So everybody should be muted during the talks. And if you have any question, just raise your hand in the participants window. I will get back to you. And for speakers, please during the talk, have your camera on. Just a reminder that the time is 25 minutes for the talk and 5 minutes for questions. And I will be sending reminders to speakers in the chat window with the reminder of time. So if you are a speaker, please check the chat window for the reminder about the time. Okay, so without further ado, let me introduce the first speaker of today's session, which is Professor Janusz Gluza. And please share the screen. Is Professor Gluza here? Okay, excellent. Yeah, please unmute yourself and turn on the camera.
Hello.
Okay, great. Okay, so Professor Gluza will talk about electroweak precision, pseudo-observables at the E plus E minus Z resonance region. Thank you.
Can you hear me now?
Yes.
Okay, so good afternoon, everybody. And I will today talk about electroweak precision pseudo-observables at the E plus E minus Z resonance region. And this is the outline of my talk. So first I will give you some literature which is based on, and then I will talk about formalism very shortly and what I will discuss and not discuss, because this is a quite broad area of activity in precision calculations. Then I will talk about motivation for precision measurements at future colliders, which is especially important. Then I will go to results which we obtained in last years for complete two-loop calculations in the standard model, and then go to the issue which is important of theoretical errors and needs for going beyond two-loop level. So for free loop calculations, I will talk about where we stand with methods and tools. And finally, I will give summary and outlook. I have 61 pages, but most of them are at backup slides. So I will base it on some reports. This is the first one from the conference in '89. In 2008, 2018, and it was published in 2019 as a CERN Yellow Report. And it gives some basics on the FCC requirements and theory at the so-called TeraZ resonance, which I will explain at the moment what it means. And other important works for this talk are report number 2 for the next workshop and yellow report, which was published in this year. Then I will give some extractions from input to the European Strategy Particle Physics meeting, which we made. Similarly for some work on theoretical uncertainties for electroweak and Higgs boson precision measurements. And finally, report 5 for input to the European strategy on the FCC-EE collider itself. And coming to the precision calculations, this is a whole set of literature which we have here. You see it is at n low, so two-loop calculations. We have many papers based on precision studies in the standard model, and final one which we have here is, let me put it in presentation mode. It should be okay. It is the work by I will mostly talk about the two papers here about on bosonic, so-called bosonic corrections, and then on free loop level. This is not much, but last one is by Chen and Iris Freitas. So about rough estimate what we are talking about, we have very complicated environment for E plus E minus studies going into some fermion states, final states. And what is inside is very complicated, which we have in this dashed frame with virtual effects of all this sort, and also external with some emissions from QED of pair of fermions or QCD or some photons themselves. So to come into real estimate of effects which are connected with some particles which are virtual, we have to take a lot of studies. And first of all, we have to extract all these emissions and of external radiations of photons and so on. And if we have it already, then we have pure virtual corrections. And here I note photons and Z bosons, which are the main because we are at the Z resonance part. And what is also important in this is the square here, which is for so-called box contributions. So this is connected with non-factorizable corrections. So we cannot just split initial and final states, but they are connected. So the main problem is how to extract something what is connected with one vertex. This is quite very complicated. And first what we have to do, we have to take and extract all these external things. This is made by Monte Carlo generators. One of most important at lab time, and which is modified all time, is KKMC by Staszek Jadach. And then we are already at this stage of virtual processes. Please note that we can have also something more than gamma Z. We can have, for instance, Z primes, so other resonances or of resonance particles. So we have to also include properly some corrections connected with this background from our particles, and this is usually made in so-called S-theory approach. So just about basic electroic pseudo-observables. We call it pseudo-observables because of that we have to remove all these real emissions from external particles which are connected especially with QED. And we have, I will focus on Z boson decay width. And we have some more like ratios of decayed widths for leptons and quarks, or forward-backward asymmetries. Just to show how what we are doing, we take, for instance, vertex, which has many contributions. We call them fermionic or bosonic or planar or non-planar. The most complicated are between the simplest are fermionic and planar, and more complicated bosonic and non-planar, like this. And then we try to extract vector and axial parts of these contributions order by order. And for instance, when we measure some forward-backward, for instance, asymmetry, we can extract axial and vector strengths, but it is up to some corrections of non-factorizable terms, which is very complicated. And on the other hand, we can take a ratio of these couplings and connect it with, for instance, definition of so-called sine squared theta Weinberg mixing angle. So this is a basic thing how we go from the electroic pseudo-observables and measurements to electroic definitions. So we now take and focus on loop corrections as here. And I will talk today about fermionic contributions, which are like these loops here at the two loop level. And what we made lately is the last row, which are so-called bosonic contributions. Usually we take, because they are easier, fermionic, and then we take bosonic contributions. Just some general remarks on usefulness of this electroic pseudo-observables. I put here some of them. And the most important is that, as you could see, we can extract pure vertices connected with electroic pseudo-observables by in a controllable way, removing QED and QCD external emissions of pairs and so on, of photons. And what is also important, that we can make comparisons and combinations of results from different experiments in this way, because we have somehow theoretically model independent calculations within standard model. Okay. So I will not discuss in this talk issues connected with LHC. Which is quite also interesting, because LHC is more and more precise. And I will not connect electroic pseudo-observables to beyond standard model effects. You can find it in this talk by Sven Heinemeier, for instance, from SNOWMAS. And I will not talk about extraction of non-factorizable corrections and QED summation and so on. And this is a domain of, as I said, Jadach and his group in Krakow. So motivation is simple. If you see this plot and this arrow here, When we have luminosity and at FCCEE, we can get a huge luminosity of Z bosons, which is normally at lab cumulative was 15 millions of them, and here we have something like 10 to 12. So this is how we call it about tera Z, because we have tera Z bosons which will be produced at this level. More you can see about experimental in this poster and ICHEP by Alan Blondel. And here is there are numbers for this. So in the Z called Z mode of FCCEE, it will be about 10 to 12 visible Z decays. So this is a huge number, and that is why it is precise. And so FCC is actually the most demanding high energy physics project for theoretical standard model calculations. And just to start with and show something to compare and how difficult it is. So the error now for experiment is from lab for Z boson decay width, for instance, it is 2.3 MeV. And theoretical error at the moment is at the level of 0.4 MeV. It is after our calculations have been done in last years. And before at lab, it was 0.5 MeV. So it means that only we gain only 0.1 MeV by taking the complete bosonic corrections at the tool loop level. So it seems, it shows how difficult it is. Moreover, as was announced by Patrick Jeannot at FCC Week in Brussels last year, they even want to make them better measurement in future FCCEE, which will be 25 keV. So you see that the difference is still big, and we need better, by more or less one order of magnitude, better calculations of and precision on theoretical ground. So how to get such precision? We just assume that we unfolded this electroweak pseudo observables properly and adjusted all corrections taking into account non-factorizable effects, and then we can calculate comfortable standard model corrections. And here are some results which follow. For instance, when we calculate sine squared theta for the big work, when we calculated it, with two-loop calculations, and we got amount which is at the level of 10 to minus 4. So just to compare it to our results, so as I said, fermionic contributions are here much bigger, about 4 times. And we have a full stabilization at the error at the level of 10 to minus 3, which is very important. Please note also that it took about 30 years from 1986, when first vertex at one loop was considered for Z boson decay. So next, I just flash some other results which we made for instance, cross-section, total hadronic cross-sections with alpha bosonic, and for ratios of leptonic and quarks as a result. And here is the main focus, which I would like to spend a little bit time on that what we got, the result is at the level of 0.5 MeV. So if you remember, this is the experimental error which FCC we would like to have is 0.1 MeV. So still we are not so good. And also CEPC, Chinese, they want to be at the level of 0.8 MeV. So for this Chinese collider, it would be already okay. The same would be for ILC. But for FCCEE, we are still about 5 times of the precision. And also important is that the first estimations of errors from bosonic contributions were at the level of 0.1 MeV. So estimations were 5 times underestimated. The result was quite bigger. So it's again shows that we have to calculate it precisely because all estimations are not so exact. And we got some results which are usually taken into some fit with some parameters, and this you can find in this all two-loop publications which were done recently for all electroweak pseudo-observables and also for form factors. So now coming to the main point, which is important also about theoretical errors, which were reported in report 1 and 4. And actually, this is a very difficult to find some knowledge about higher order corrections based on what we have now. And this, what we estimate usually is the amount of a total correction of a higher loop level. And real calculations gives us a concrete number with a much better error. So this is important that it is a difference. When we calculate, we have no any problem anymore. And here is an example how we make estimations. For instance, if we want to estimate at the free loop level, what would be when we know at the two loop level, then all calculations are split into few of them, and then we get different approximations, and all together is what I said, we get something at the level of 0.5 or 0.4. And bosonic corrections, which were before our calculations, they were estimated at the level of 0.1, just on the one loop level squared. So you see the difference between this and real calculation were quite different. So at two loop, we maintained 4 digits of precision in calculations, and this is good for, and it means also that if we calculate at free loop, let's say some correction, which will be with the total 2 digits accuracies of 10% accuracy only, this will be enough, because then we will be at the one level order lower, so we will get estimation at free loop at the level of 0.04 MeV, which is smaller than what experimentalists need, 0.1 MeV. So it means that it just shows that we should make this all free loop calculations properly. And here is the summation again for this studies. As I said, with proper estimate what we have with different methods for free loop and higher orders, we can be below what experiments need for this in future, in let's say 20 years for FCC-EE, and we can get it with this precision. So proper preparation of future colliders needs calculations at free loop order, and it also needs a proper numerical approach. And we have two such now precise calculations with sector decomposition method and Mellin-Barnes method. We made it both in Euclidean and also in physical Minkowskian space. And we get accuracy for each integral at the level of 2 to -8, so 8 digits. It is really excellent. In Minkowskian region, we can get, so physical region with all the thresholds and so on, we can already get so good accuracy. And moreover, it works for hard threshold on-shell cases, especially good for Mellin bands, and for sector decomposition, more useful are integrals with, it is sector decomposition is more useful for integrals with many internal masses. So we have many scales here. This is non-trivial. At 2 loop, and if you put here some other leg, you will get internal leg, you will have 3 loops. And we have more or less one order of of more diagrams in comparison with 2 loop. So precision must be sustained. Here is an example of progress for sector decomposition. For instance, when we compare in Minkowskian, so physical region, we have analytical result, and you see even in 2016 or 17, it was quite poor result, and now we can get already 3 or 4 digits. This is for very specific diagrams where most of legs are internal propagators are massless. And for Mellin bands, we have a new method with quasi-Monte Carlo integrals where we can get into integrals which are even 5 and more dimensional, and we get quite good precision with some relatively small number of points. So we have perspective to do it, and to summarize, challenges for the Z-pole which we have now is that we should calculate 3-loop electroweak and mixed electroweak QCD corrections for Z boson decay vertices. We should also implement leading QCD for loop effects, and we should understand QED interference effects and non-factorizable corrections. And properly should be adjusted Monte Carlo generators at 2-loop and beyond level. And this should, it would be very good and to have independent generators from what we have now after lab. And finally, new in the what is also here important, this is connected with factorization to infinite order of multi-loop photon soft virtual QED contributions, and we have to disentangle QED and electroweak corrections beyond 1 loop with soft photon and factor resummations. And what I said at the beginning, finally, we should also implement for proper preparation of next colliders, higher loop effects with proper Lorentz series around the Z peak. So this is my end of the talk. Thank you for hearing me, and what.
Okay, thank you very much for an interesting talk.
Yeah, I can see the chat now.
Any questions for Professor Gluza?
I mean, I will put my. Okay. Hello.
Questions? Comments? Well, if not, then thanks, Professor Gluza, again. And we will move to the next talk. So, Professor Ward, can you please share your slides?
Yes, I think I just did. Is it being,
okay, yeah.
Can you see it?
Yeah, we can see it. Yeah, if you can.
Switch the view to full screen. Okay. Thank you very much for the opportunity to, let's see, I guess I forgot to put my camera on.
Yeah, if you can turn on your camera
Just
just for the talk.
Just a minute. Let me do that. The camera. Just a minute. Oh, here. Okay. The camera starting. Okay, now.
Okay, excellent. So the next talk is by Professor Ward from Baylor University about the theory of recent quantum gravity. Please.
Okay, thanks for the opportunity to speak. And the talk will go according to this outline. I'll speak some introductory remarks, and then I will give some overview of the theory, which isn't very familiar, and turns to some of the applications, phenomenological applications in Planck scale cosmology, an estimate of the cosmological constant and some of its questions that it raises. And finally, time permits, I'll have some comments on the implications for SUSY gut theories, which are rather somewhat indirect. And it all goes to the question of resummation in quantum field theory, because there's an ongoing discussion. Normally we have, this is the usual geometric series type of thing, but in field theory, we can do exact resummations of the kind I'm going to be talking about, in which we don't drop anything, or we can do approximate ones in which things are dropped, but these are then still accurate up to some fixed order. And classically, this started in E plus E minus with Jackson and Shari as an example of this second case, and Unifranchiseur is an example of the first one. And remarkably, long-going arguments about which is to be preferred, starting with discussions we had with Fritz Behrens starting in 1988 in these meetings. So you get some idea how long these arguments have been going, and I suppose they'll be going on after I'm dead in my grave as well. And nonetheless, today I'll talk about how it led me into the gravitational theory. And you never really win or solve. I don't think it's such a thing as winning or losing these arguments. They just continue. But the basic point is, do you limit or enhance the fixed order exactness that you can arrive? And it's a long story, and we never really resolved it. And as I say, I don't think it will be resolved when I'm dead in my grave. But it's good for physics. Now, when we go to quantum gravity, we have the same kinds of things coming around, because the question is, can you calculate it? If you do naive estimates on the powers of the fields and the derivatives you get, if you take Einstein-Hilbert, you would naively guess you can't do it in an ordinary field theory, which is why people have gone historically to strings. Which gives a one-dimensional object a Planck length, and therefore they cut off any problem with UV. And you give up the idea of point particle physics. You get solutions. Unfortunately, this is an underestimate. That number is much bigger than that. And so you end up with an anthropicity position, which I find unappealing, but others do not. You can go to the loop theory. In that case, you also give up on point particle physics, but you have loop structure at Planck scale lengths. And it has suspected UV finiteness, linear rise, quantum gravity constraints, et cetera. It's a debate whether there's some outstanding issues in the theory or not. And again, that debate will probably go on for a while. You can give all of that beautiful symmetry at Planck scale lengths up and look into this overall Lenshift type of idea where you change the scaling between space and time at Planck, in the Planck regime, so that your propagators get an extra term, and which makes the theory power counting renormalizable, but you don't have Lorentz invariance. Lorentz invariance is some kind of accident of low energies. And there are other pathologies there, which I won't go into. I try to do something much more conservative. I try to take Feynman's work from the 60s in Poland, and I try to develop it by just doing the calculation in the Rissam formulation. So it's a very conservative in that sense, because I'm not adding anything. I'm not saying that we lose Lorentz invariance at Planck scale lengths. I'm not saying that I've got loops or strings or whatever. I'm saying that if I do the calculation a little better, I can make sense out of the theory. So now what kind of sense am I talking about? Well, I'm talking about UV finiteness. I'm talking about constraining SUSY, perhaps. I'm talking about predicting the value of the cosmological constant with what I would say is a relatively small theoretical uncertainty. I mean, it's in gravitational physics. I think on gravitational physics standards, it is small. It does not, it's not out there alone. It's consistent with Weinberg's asymptotic safety odds, and as it is realized by the exact field space renormalization group program of Reuter and his various collaborators. It is consistent with Kreimer's leg renormalizability results, so that you show that, well, if you do naive counting, you don't have a normalizable theory, but if you look at the legs and look at how many independent infinities you have associated with different legs, you can show that you have renormalizability in the terms of if you count independent infinities per leg in some way of talking. So leg renormalizability, as he likes to call it. And I just want to talk a little bit today about where the theory stands, because I realize it's not very popular, and in fact, in general, it's not well known. It's not only that it's not popular, it's not well known. Now, like I said, it starts from a relatively conservative position. So I take something Feynman wrote down. See, I have here in 1963. He was in Poland, I think, giving lectures, and somebody took notes for the lectures, and this article is a result of that. And so you take, I'll take just a scalar, but you could put other particles, but since we're just trying to see if we can calculate with this R present, putting any kind of matter here is good enough. So this is a scalar field, and as you see, this thing, because it has to be generally covariant, this is an infinite number of terms that we're looking at here, if you expand them all out. And in there, I had used his notation, so that's the derivative. This is, the metric is written with a quantum piece scaled by kappa, square root of A pi g, and then and then this is some of the notational convenience used to make the expressions a little tidier. And you need to pick a gauge, and this is this gauge that Feynman chose. So I just do that. So I just take what Feynman did. I don't change it. The idea is that it's just another quantum field theory where the metric now has quantum fluctuations as well. Did I go backwards? I didn't mean to. Okay. Now, the first time you try to calculate even just one loop, you see the problem with it because the vertices have an extra power of k in them compared to most theories that we know, vector building theories, for example, and therefore all these integrals don't really exist because of ultraviolet problems. And you need to do something about that. And like I said, I showed you some examples of what people have done about it. They've made superstring theories. They've made loop quantum gravity theories. They made Harvard lift shift type theories. Here, I try to resum the theory. So I take a formula that Yeni wrote. There it is. Let's just take a fermion propagator. This is what happens if you resum the infrared part of the propagator. This is the infrared emission, as you can see. I just have 2K mu here. And in the case of quantum gravity, an extra K appears for all these vertices because of the spin 2 nature, and this formula gets changed to what we see here. And this has the property that when you do the integral, and I just take a scalar, but the same thing happens with any spin. It has the property that when you do this integral, you see you have an extra power of K squared out in front of what would have been just a logarithm that came from the integral if you were doing it in an ordinary field theory. That would just give you a logarithm. And you therefore end up with the fact that this thing is damped faster than any power of K that you could get from Feynman diagrams. So you see, if you look at all that infinite series of terms I had, for any finite quantum correction, you will have a finite number of powers of K in the numerators of your integrals, and this exponential will make them all converge. So, as I explained here, so therefore the theory has gone from being completely out of control to being one of the nicest ones we could have. Of course, it has some algebra you have to keep up with, but you can use a computer for that. That's not the problem. Now, I want to point out that Dr. Weinberg already, you see, in '65, I have it here, went through a similar kind of exercise, and he showed that the infrared part of gravitational virtual exchanges generates exactly this type of damping in the large UV. Of course, he didn't use it in that way, but if you take his formulas, they reproduce this. They just reproduce this result. Now, he has formulated the asymptotic safety idea in which, so we get this behavior for the running Newton's constant, and this leads to a fixed point behavior just as described by, used by Borno and Roydo and as postulated by Weinberg. Weinberg did not have any he didn't try to write down a dynamical system that would give asymptotic safety, but he postulated that that could be a possible way that gravity UV gets tamed, namely that there's a finite dimensional critical surface that's attractive in the UV. And we have a number of immediate consequences. Elementary particles, for example, if you take our results for this running constant, you'll see that they have no horizon, and that also agrees with Bonanno and Reuter, as long as the mass is less than the mass of the Planck mass. And the basic physics is that the gravitational running constant vanishes as in the UV. That's the basic physics of it. Now, if you go into the cosmology, we follow Bonanno and Reuter. Here's the paper with the Einstein-Hilbert starting point. And the idea is that you incorporate the fact that the Newton's constant is running and cosmological constant is running. You put all of that into the cosmology is the idea. And so you get a different set of Friedman equations where you have some extra dots in here that would be zero in an ordinary. See this, that would be all zero, et cetera. And there is one kind of ansatz, and so if you, and this is a Robertson-Walker metric that you want to use that with. And this is your usual equation of state formula. Now, there's one part of it that you have to have some way of talking about this running so that you relate the K to some time, because it is, and it's this, this is the ansatz that Reuter and Vinorno have used. Following, I'm going to add Sola's group's suggestion, where this constant then is something that has to be determined from solving the theory. Now, if you take this and you want to, we believe we're close to the K equals 0 type of Friedman equations, and so you have a regime from t equals 0 up to some t class where you're in the Planck regime, and then and you expect this to be a few times the Planck time, where you join on smoothly to this classical. We call it T class because you join smoothly at that point to the Friedman-Robinson-Walker phenomenology. And they show that all the problems, horizon, flatness, scale-free Harrison-Dovettor spectrum, entropy problems, all solved by Planck scale quantum physics. So it's a pretty impressive scenario. It's phenomenological in the sense that the results depend on the cutoffs in the Reuter theoretical field space renormalization group program for the theory. The main point for the analysis is that these limits on the running constant, Newton's constant, and the running cosmological constant dimensionless parameters that they remain, that they're positive in the product is basically cutoff or threshold function independent. Now, what we do is we predict that these don't have cutoff dependencies because we just get them as predictions from the theory. And we can estimate, therefore, lambda, because we can start at the place where it switches over to this Friedman term, Friedman formula, and then we can use the standard cosmological equations to evolve it down to where we are today for the age of the universe, this T0. And remarkably, this generalized Witten index for the cosmological constants we put in, this is coming from the calculation that we do for the cosmological contribution of energy to the cosmological constant from a given species. If we put the numbers in remarkably, and this is still hard for me to believe because I have to tell you, I'm right on the, I mean, this is the measured value, so-called measured value that you see, and this is what came out of this calculation. It's quite, I mean, even if it is an accident, it's quite really, I haven't even been able to do that in the standard model very often on some calculation. And so there's some issues when you get something like that, you owe yourself at least to try to criticize it. Well, maybe there is something wrong with it. So let's see. We don't really know these transition temperatures, time, I'm sorry. We took it from Bonner and Reuter, this T classical switch, which was 25 over M Planck. It could be off by some factor of order of 100. for example. That's one criticism that people can make. So I did try to look into that a little bit. I used some de Sitter space solutions from DER to get, so I saw, in other words, these are the field equations in de Sitter space for field theory. It was solved by DER et al. And so we can ask the question what the Heisenberg uncertainty principle says in those solutions, and we get some restriction, you see, because you can imagine if you have some curved paths, geodesic, these solutions are saying that in a given amount of time, you can only go so far on that geodesic, and that can be turned in. But remember I have a relationship between the time and K, so I can get a restriction from the uncertainty principle. And so we work that out, and I get the delta Q that goes in the uncertainty principle is 1/5 of this, delta Q squared, I'm sorry, 1/5 of this characteristic description of the curvature in the theory, if you will. And surprisingly, if I take the condition that when this fails, is where I have to stop Planck scale inflation, because remember, that's where I want to switch over to the Friedman-Robinson-Walker. I come out with exactly this this 25 that I had previously. So okay. Again, this is the uncertainty argument. We know we can have factors of order unity around. So, but I now claim that my prediction is more off by factors of order 10 rather than being off by 100, let's say. So I'm claiming that I did reduce that question, although I have not solved it. If I go to Susie, guys, I hope you can see this. I need to. This is the type of thing that one is getting because of what you see. Normally, you don't have any limit on this energy of vacuum energy, but I do because of those Brisson propagators. I hope we can see this. Now, Mohapatra has, Devin Mohapatra, I'll just take their example. There, you can take any, I just take this one. I like it because it has right-handed sector. It's a point where it has both left and right-handed bosons in it. And so I have a stage where I break the right, and then I down to the normal SU2 left cross U1. And so it's still all supersymmetric. And then finally I break the SUSY, what I'm going to call the weak breaking scale. So I'll go down to U1 SU. U1 electromagnetic plus SU3 color. Now, these masses which I took, the LHC is making some of this unfavored, but I'll just use them for today. And I have some choice in where I put, this is the gravitino. There's some freedom in that. And things change a little bit if I do that. But just you see, so these kind of numbers for the gluino, I have 1.5 TV, where they're just about, okay, there's some space for that left, et cetera. These things are all, these are still probably okay, but this is, if the LHC continues the way it is, all this what I have here will have to be changed. Okay, but the main point I want to make, so the model, by now, if you do all LHC constraint, probably this model is dead, but what I want to point out is that because of the extra SUSY particles, I get some new contributions to lambda. And so this formula that I have here, and those other factors are not changed, this index factor gets a contribution that instead of, that's non-trivial on the scale of what we had, you see. And essentially I need this to vanish because this is the change away from my beautiful prediction that I had, 2.4 10 minutes. Yeah, I need that to go away. Now, to get it to go away, well, since it's positive, I can get it to go away by putting the gravitino at a very high mass to make it have a large contribution. And I need to put it up near, well, okay, within 1/20th of the gut scale. And that will allow me to adjust it away. Or the one I like better is I can make a new whirl, of course, at very high energy, so 10 to the 3 TeV for the new quarks and leptons versus what they have now. And then the partners, the SUSY partners are relatively light. So now we would have two sets of supersymmetric particles that we're looking for. The ones that go with the ordinary standard model, which we have not seen anyway. And now I'm adding a new copy of all the quarks and leptons, but flipped so that they're higher than their superpartners, which are also, and you see, this is also getting close to being ruled out. But we could always move it up, as you know, with these models. It's just not difficult to do that. And then this would also cause that to cancel, it turns out, well enough. So those are the two ways. And I rather like this second one because it predicts that there's a lot more new particles, basically. There's another whole copy of what we call standard model-like particles at very high energies, 10 to the 3 TeV or so. And then there's a whole new set of SUSY partners that they need that are very much lighter than that, in addition to the supersymmetric particles that we have not seen one trace of as far as we can see so far. Well, with that kind of prediction, let me just say that there are the other theoretical issues, other contributions of vacuum energy are small on the scale of what I calculated, so we drop them, they don't change anything. And there's some covariance issues with the Bianchi identity, which forces you into a more general form of the new Friedman equations, if you will. And it was the one that I actually used for my calculations. And this is discussed in these papers, Sola and his people. So I'm done. I try to give you kind of a quick overview of the fact that it looks like quantum field theory can have control over the electroweak, the QCD, and the quantum gravity. Now you have to understand, you're looking at, a man is talking to you that came into physics in graduate school in 1970 at a time when even this here that I have this thing on was in grave doubt. There was a significant part of the particle theory community that did not believe quantum field theory would ever describe correctly the electroweak interaction. And they had completely just about given up on the strong interaction. So when I entered physics, none of this, what I have on this top line, was accepted to be describable by relativistic quantum field theory. I mean, it just wasn't. You almost had to apologize in some places. Now I have all three of them up here. Gravity would have been unheard of to suggest that. And it's all about controlling the infrared, collinear, and UV limits. If we have control over these three limits of the theory, it looks like we can understand even something as fundamental as the cosmological constant. Thank you very much.
Thank you for a nice talk. Any questions? Please raise your hand. So I have a question. In the beginning, you did this analysis of the propagator normalization. But what about like for graviton scattering? So famously that diverged two loops. So yeah, how would you treat that?
What I said was, it's not even just full graviton. There's plenty of I showed a propagator, but if you look at any loop contribution in the theory, whether you have it's 4 gravitons or whatever, those propagators are resummed so that in the UV, you do the whole thing, you Wick rotated the whole thing in Euclidean space once you get the integral you want to do. And the propagators are damped exponentially at very large UV momenta. So the thing goes from being uncontrollable, which is what you're talking about, to being finite. I mean, the exponentially damped propagators remove all UV divergences from the theory. Because in any Feynman series, each graph only has a finite number of propagators and vertices, and each one of those vertices has only a finite number of powers of k in it. And the exponential kills every finite power that it's up against. It doesn't matter if you, the only way you can beat it is if you go, you know, if you what the question you can ask me is when I add all that up, does it converge? In other words, suppose I was able to do every one of them and put them all together and add them, would they be finite? Now, that's a question I don't know the answer to. I don't know the answer to that.
Okay, thank you. More questions? So if not, thanks, Professor Ward, again. And we move to the next talk.
Okay, so I need to unstop sharing.
Yeah, you have to stop sharing this. Yeah, exactly.
Let me see. Just
thank you.
Where is? Oh, it's up here. Yeah. Okay. So I have to stop. Let's see. Stop to share. Stop share. Okay, there I am. Now you have it.
Yes. Great. Thank you. So next speaker, Oliver Witzel. Please share your slides.
Are you seeing them now?
Okay. So the next is, yes. Please turn on your camera.
Okay.
Yes.
Can you hear me?
Okay.
Oh.
So the next speaker is, yeah, we can hear you. Great. Next speaker is Oliver Witzel from University of Colorado, and he will talk about composite Higgs scenario in mass split models. Please.
Thank you. Yeah, I'm going to basically cover our publication from earlier this month. The reference is given only on the title page here on the top. And I will, in contrast to the previous talk, try to focus on one specific problem. So we are specifically looking at the composite Higgs scenario, and I will introduce our approach to solving this by using mass split models. Now, to start simple, the general idea is we take the standard model and we extend it by a new strongly coupled gauge fermion system. And then from this new strongly coupled gauge fermion system, the Higgs boson arises as a bound state of the new sector. Mass and quantum numbers have to match the experimental values, of course, but only after you account for all the standard model interactions and corrections. So that basically boils down to the constraint that we need to have a large separation of scale in our model to explain that we have seen a relatively light 125 GeV Higgs boson, but so far no other states have been detected in the experiments. This gives us an indication that the system cannot be QCD-like, and there are constraints, for example, coming from the generation of quark masses, which quite strongly rule out QCD as a viable strongly coupled sectors, or properties of the strongly coupled sectors, I should say. Basically, the conjectures are that such a new strongly coupled sector needs to be a near conformal gauge theory. And of course, we then need to build in mechanism to generate the masses for the standard model fermions and gauge bosons. And at some point, of course, also need to test the agreement with electroweak precision constraints like the S parameter. Writing things down more in a formal way, the idea is that we want to describe the standard model and a whole zoo of new particles coming from some new physics. And we do so by starting with the Higgsless and massless standard model, which I indicate by the Lagrangian for SM0. And then we want to add the new strongly interacting sectors, so SD for strong dynamics, plus some interaction term. And with these ingredients, we would like to explain, we have a theory to give mass to the standard model fermions and the standard model gauge fields. Presumably for the fermions, we will have some for fermion interactions or partial compositeness. The new strongly coupled sector itself also has fermions and interactions, but we just take, they are given from some higher energy scale indicated by the Lagrangian LUV. And we are not really addressing where this is coming from. We are just trying to solve the problem of having a standard model with the electroweak sector and the Higgs boson. And for the remainder of this talk, I will focus on the new strong dynamics in isolation. So we are not yet studying the interaction terms. That is a step for the future. In this scenario, the Higgs boson is a composite object, and there are basically two scenarios for it. One, more in the traditional Technicolor spirit, it would be a dilaton-like particle. So the Higgs boson of the strong interactions would be an isosinglet scalar 0++. In that scenario, the scale has to be set by the pseudoscalar decay constant of the strong sector being equal to the vacuum expectation value of the standard model. So you're roughly having a scale of 250 GeV. In the ideal scenario, you would assume you have two massless flavors because this gives you exactly 3 Goldstone bosons, and they are then eaten to get the longitudinal components of the W+ and the Z boson. The alternative scenario assumes the Higgs boson to be a pseudo-Nambu Goldstone boson. So this is more in the idea of a pion and QCD. So this new strong sector has spontaneous breaking of the flavor symmetry. And that gives rise to the PNGBs. For this, you need more than 3 flavors. The mass of these pseudo-Nambu Goldstone boson Higgs arises solely from the interactions. And the vacuum alignment is non-trivial. So you would relate the decay constant of the strong sector to the standard model vacuum expectation value divided by the vacuum alignment angle chi. So this gives you one parameter more freedom to move away any unwanted states or any unseen states so far so they could live at higher energies. Now with the mass split model I'm going to introduce on the coming slides, we can basically accommodate those scenarios. For the dilaton-like picture, we would need to find a light 0++ state, which has a mass similar of the pseudoscalar and lighter than the vector state. And in the scenario of the pseudo-Nambu Goldstone bosons, you can embed it, for example, into the fundamental composite 2 Higgs doublet model worked out by Ma and Cachapaya. The philosophy behind mass split models is that promising candidates are chirally broken in the infrared, but conformal in the ultraviolet. So if we start from a chirally broken, let me stop back. So we are starting with a mass split model, and we are choosing, for example, an SU3 gauge theory, and now we have heavy and light or massless fundamental flavors. And if we start from the 4th flavor light sector, that is chirally broken in the infrared, then we add to the system a number and age of heavy flavors to push the system near an infrared fixed point of a conformal theory. As I said before, the light sector can be connected to the 2 Higgs doublet model, whereas the heavy flavors themselves could be invisible to the standard model. So you would only see part of the spectral quantities these this mass split system has in the present day detectors. Let me summarize on this page the general paradigm for this mass split system, and in the subsequent pages I will give you more evidence and more details on how this arrives. But it is important to keep in mind we are looking for a system which is not QCD-like, and it should not surprise us that it is indeed having properties which are rather different from QCD. So in QCD, we typically take the continuum limit by tuning the gauge coupling to 0 and take the chiral limit by sending the fermion mass to 0. If you think of a conformal theory where you have to generate NF flavors, presumably you will have to simulate it as a mass-deformed conformal theory, which exhibits an infrared fixed point. You know that all masses, all ratios of heteromasses scale with the anomalous dimension, and you take the continuum limit by sending the fermion mass to 0. This scaling of the ratio of heteromasses is called hyperscaling. Now, mass split models live in the attraction of the infrared fixed point corresponding to the degenerate NF flavors, and they inherit the hyperscaling, but they are still chirally broken. And that leads to the special relation that you take the continuum limit by tuning the heavy flavor mass to 0, keeping the ratio of the flavor masses fixed, whereas the chiral limit is taken by sending the light flavor mass to 0, and the ratio goes to 0, too. In this system, the gauge coupling is basically irrelevant. It takes the infrared fixed point values, and it is a highly determined system. You have no free parameters after taking chiral and continuum limit, but you have a large number of light, heavy, and heavy bound states, which at some point would need to be found in the big experiments. As I indicated already, we are doing numerical simulations to study the systems, and we are referring to standard tools of lattice field theories. So we are discretizing space-time and do Wick rotation to work in Euclidean time. And as I said, we are simulating an SU3 gauge system with 4 light and 6 heavy flavors. And that is the basic for all the data I'm going to show subsequently. And for the experts, there are some more technical details on this slide. Now, as I tried to outline already in the introduction, the key property of the system is hyperscaling. We can use simple arguments from Wilsonian renormalization group to derive the property of hyperscaling. And the basic setup is that in the ultraviolet, our 2 fermion masses, ML and MH, are living below the cutoff. The cutoff is given by 1 over the lattice spacing. And for the simulations, we also know that the light and the heavy flavor masses have to be less than 1. Now, when we lower the energy scale mu from the cutoff, our G-float lattice action moves in the infinite parameter action space, and this move is dictated by the fixed point structure of the conformal theory with NF flavors. In this setup, the masses scale according to their scaling dimension, and this is the scaling dimension is named Ym. And we assume that all masses are still so small that the system remains close to the conformal critical surface. This means only the masses change under the RG flow, and the gauge couplings take their infrared fixed point values. Now you can derive how physical quantities with mass dimension are scaling, and the basic equation, which is central to the rest of this talk, is given on the bottom in red, where let me put it on the next slide, where we basically have AMH, which is a lattice hadron-mass, basically any quantity which has a mass dimension. So think of it as a pseudoscalar meson mass, the vector meson mass, equally well the pseudoscalar decay constant, or the lattice space, or the inverse lattice spacing to be precise. MH is the lattice fermion mass, ym is the scaling dimension, 1 plus gamma star m, the anomalous dimension, and the capital phi h is just some function which only depends on the ratio of the light over the heavy flavor masses. Now, if you look at that equation and you can consider that you have two different hadrons, you can form a ratio as it's shown on the right. And if you do that, the first term drops out and you're just observing that the ratio of hadron masses only depends on a function depending on ml over mh. Now, this is already rather magic, and let me give you numerical evidence that this is indeed the case. So on these sets of plots here, I'm showing you different meson states. From left to right, we have the pseudoscalar, the vector, the scalar, and the axial. On the x-axis, I always show the ratio of light over heavy flavor masses. And then you have the shaded symbol at the bottom, which is on the case for the leftmost plot, the light pseudoscalar. Then I have on top of that the open symbols, the heavy light pseudoscalar, and on top of that, the heavy pseudoscalar with the filled symbols. So with light, heavy light, and heavy, I'm always referring to the valence quark content. And the remarkable fact is that you see the different colors and shape of the symbols. The blue squares correspond to using a heavy flavor mass of 0.2, the orange triangles, a heavy flavor mass of 0.175, and the red circles, 0.15. Now, irrespectively of changing the heavy flavor mass, they trace out unique curves in ml over mh. mh itself has no impact on the value. It is only the relevant quantity is the ratio of the two flavor masses. And you see that for the pseudoscalar, the vector, the scalar, or the axial. And since our data are so remarkably impressive, I even dared to look at the tensor state, shown on the next slide on the left. Or we also can look at the spin 1/2 and spin 3/2 baryon states, where then on the bottom, only light quarks are forming the baryon, or only heavy quarks are on the top, and the open symbols have a mixture of heavy and light. Now, this is the first very strong indication that this system is indeed living close to the conformal fixed point and observes hyperscaling, but we can actually do better. If you recall, this was the original equation for hyperscaling, where we had a single quantity and we have the scaling to the anomalous, to the scaling dimension of the mass scaling, the power of the scaling dimension. Now, in this case, I'm using the inverse lattice spacing determined with the so-called gradient flow scheme, square root 80 as the quantity I'm looking at on the left-hand side. And this is the quantity which is shown in the upper panel of the plot on the right. So we have our data sets with different values of the heavy flavor mass. On top, there is the blue data points corresponding to, again, to MH.2. Then we have the orange with 0.175 and the blue with 0.15. As you can see, they are all forming a very linear behavior. So that suggests that if we want to determine this scaling dimension ym, we can make a simple polynomial ansatz for the function phi h. And in this case, I'm using simply a quadratic polynomial. So we have 3 coefficients plus the exponent ym we are trying to fit to all the 17 data points which are shown. And if we do that, we determine the scaling dimension ym to be 1.47. Now, if I do that, I can draw these fit lines on the top plot, but I can also multiply mh to the power of 1 over ym. And suddenly we do see hyperscaling and everything collapsing on top of each other on the lower plot, where this is included in the fit. Now, the fit is the same. This is the value which corresponds to our value of ym. And we can moreover read off the value in the chiral limit for this functional form phi h, which has a value of 0.48. It will be relevant later on. Now, as I said, we can do that with any quantity. So let me show you another example. This is the pseudoscalar decay constant. It's a similar polynomial ansatz. However, here I'm using, again, the light data shown by the shaded symbols on the lowest line. The open symbols refer to the heavy light pseudoscalar decay constants, and the heavy pseudoscalar decay constants are shown on the top. So we have 3 × 17 data, and we use a similar ansatz where we parameterize each of the curve with a quadratic fit form, and then have in addition one coefficient ym to do a combined correlated fit. And this has excellent properties. We again get the value of ym to be 1.47. And it just works beautifully. We accounting for the scaling dimension here, all the different values of mh are again sitting on top of each other. We see perfect collapse. Now, what you also see here is that the light pseudoscalar has a finite value in the chiral limit, which is the first indication that the system is indeed chirally broken as expected from the construction. Now, having shown that the system indeed exhibits hyperscaling and there are signs that it is chirally broken, the next important question is, can we derive an effective field theory to describe our data? Or is there an effective field theory to describe our data? Now, before doing that, let me first introduce the hadronic scale lambda h, which is basically given by the scale where the heavy flavors decouple and the light flavors condense and spontaneously break chiral symmetry, which is roughly given by this equation here. We can turn that equation into a scale, which we will call lambda h, to indicate the hadronic or chiral symmetry breaking. Now, if we lower the energy scale below lambda h, the gauge coupling will start running again. And that is the interesting range. Now, if we go back to the hyperscaling relation I showed for square root 18 naught, we can be actually even more specific for lambda h, because in the chiral limit, we can use a standard scaling equation to obtain this expression for A. And this term is just a number around 0.48, as mentioned before. And combining it with the equation up here, you define that the inverse scale lambda h is basically given by the chiral limit value for our lattice scale square root 18 naught times this constant. With this lambda h, having defined this lambda h, we can now continue and first take another look at the chiral limit. On the left, I'm showing the ratio of the light vector over the light pseudoscalar mass. Since the pseudoscalar mass is supposed to go to 0 in the chiral limit, this ratio has to diverge as the ratio of the flavor masses goes to 0. And as you can see, we start around a value of, well, 0.13 maybe, and it goes up to 1.7-ish. So if we would simulate further to the left, we expect a further and a steeper increase on this ratio. On the right, I'm showing the squared pseudoscalar mass over our hadronic scale lambda h. And what you expect is that in the chiral limit, there is a linear relation in the quark mass. So the ratio, so the squared pseudoscalar mass is basically linear to the ratio of the light over the heavy flavor mass. And as you can see, that is by eye very well met, but you also see that these heavier data points are clearly below a linear extrapolation of the other data sets. So there is some curvature as one would expect when you go away from the chiral limit, that you encounter correction terms. Now, what do we know about the low energy effective description? At this point, we know that in the low energy infrared limit, our system exhibits chiral symmetry breaking, and we seek an effective Lagrangian to smoothly connect from this chiral symmetry breaking range to the hyperscaling range where the standard hyperscaling relation is valid. So basically the energy scale mu equal lambda h. If we express our lattice scale in terms of lambda h, we obtain this equation up here. So that is again showing that we are only having a dependence on ml over mh. And if we are below the lambda h scale, the system reduces to the currently broken four-flavor system, where we would have a running fermion mass mf. Now we can derive from the scaling equations above that this mass mf in the four-flavor theory has to be related to the ratio of the light over the heavy flavor masses times our scale lambda h. This is the important and to some degree not that intuitive relation of having the fermion mass in the four-flavor system being directly proportional to the ratio of the flavor mass in the 4+6 system. But that is exactly what you get when you do the detailed steps of the calculation. Now, as I said before, you obtain the continuum limit, tuning mh to 0, keeping this ratio fixed. And since in the following we are looking at the low energy description, I'm only going to look at the light sector and will drop the superscript LL. A candidate theory for this low energy effective description is given by the so-called dilaton-chiral perturbation theory, which was derived by Goltermann, Shamir, Appelquist, Ingleby, and Pi. And it was originally developed for the case of an SU3 gauge theory with 8 dynamical flavors. And that theory is supposed to be just below the conformal window. And you use the separation of the 8 flavor theory to the conformal window as the expansion parameter. Numerically, it was shown by lattice simulation that this theory has a light 0++ dilaton, hence the name of the theory. And this guy, the 0++, is as light as the pseudoscalar. Now, we adapted the basic equations from dilaton-chiral perturbation theory to our mass split system, which basically means to translating the fermion mass in this dilaton chi-pt to the ratio of light over heavy flavor mass times our hadronic scale. Dilaton-chiral perturbation theory has one general scaling relation, which tells you that in low energy coefficient D0 times the pseudoscalar decay constants to the power of 2 minus the scaling dimension equals the squared pion mass over the flavor mass. And we translate that, and if you do the math right and account for the occurrence of the lattice values of A and the different locations, you end up with this equation here. And Goltermann, Neal, Shamir also assumed a special form for the dilaton potential and then derived the second scaling relation where the ratio of the squared pseudoscalar mass over the pseudoscalar decay constant is given by the scaling dimension ym times another low energy coefficients d1 times the Lambert function, which has as argument ym times d1 over d2 times the flavor mass. And again, we replace the flavor mass using this equation here to get the equations we are interested in fitting. Now, the first equation is a little bit nasty because on both sides of the equation, the pseudoscalar decay constant and the mass have statistical uncertainties which are correlated and are of the same size. We are interested in determining D0 and ym. So instead of doing a very complicated fit, I use the ym as input, as shown in the top panel. And then I can only do a simple fit to determine D0, and we get a perfect description of our data because the ym comes in with a large uncertainty. In the second panel, I do the alternative fit, and I scan a range of D0 fitting for ym and seek the value where the chi-square degree of freedom is minimal. That is more in the spirit of curve collapse, and that is shown in the lower panel and works equally well. Fitting the second equation is straightforward. You just need to implement the Lombard function. And again, you see that all the range of our data are perfectly described by Dilaton-Karl perturbation theory. Now, let me quickly come to the summary and outlook. I'm afraid I'm running out of time. Dilaton-Karl perturbation theory describes our data extremely well. And that implies that we have a light 0++ state, but we haven't measured that numerically. We will push simulations deeper into the chiral regime and also make the connection to the 10 flavor limit, study more phenologically interesting quantities, and we'll also investigate the finite temperature phase structure. Now, this is interesting because there could be a connection to gravitational waves if we identify a first order phase transition. And since I am barely out of time, let me quickly show you that we are working on that. And this is the result of a few weeks' work from a hardworking graduate student, Curtis Patterson, who together with myself and Anna have been pushing forward to this simulation. And let me leave you with a summary slide.
Okay, thank you for a nice talk. Any questions, comments? Well, I don't see any questions, so thanks the speaker again. And we will have now 15 minutes break, and we reconvene in 15 minutes at 5:15 p.m. Central European time. Okay, welcome everybody back. We will start the next section. So the next speaker is Katarzyna Jarkowska. Can you please share your slides and turn on the camera?
Yes. Okay.
Yeah, everything's fine.
Okay.
Okay.
Presentation. Okay.
So yeah, so welcome. Next speaker, Katarzyna Jarkowska, who will talk about proton decay in the minimal realistic SO10 GAT. Please.
Yeah. Yeah. So in this talk, I'll be talking about the minimal realistic non-supersymmetric SO10 grand unified theory study, which is mainly motivated by the proton decay. So first, I'll start with the introduction of SO10. So SO10 theory, this SO10 group embeds in itself the standard model KH group, which leads to the charge quantization, automatic anomaly cancellation, and also it leads to the existence of the monopole. Moreover, all the fermion fields from one generation plus right-handed neutrino can be all put it into this one 16-dimensional representation. Okay, so of course all the gauge fields for SO10 are in this 45-dimensional representation, which contains standard model gauge fields, but it also contains leptoquarks and diquarks, which bring new physics into the picture. So, for example, there are fields which mediate proton decay. So, all the features that I was describing on previous slides are common for most of the SO10 models. And what distinguishes SO10 models is the scalar sector. So the minimal renormalizable this SO10 model contains 45-dimensional scalar representation in the scalar sector. This representation breaks SO10 down to the intermediate state symmetry, then 126-dimensional representation, which breaks intermediate symmetry down to the standard model. And this representation also helps to have renormalizable Yukawa interactions. And then one is a 10-dimensional representation to break standard model, plus to have a realistic fermionic spectrum. From the part of field content that I described, it's easy to generate neutrino masses using type 1 and or type 2 seesaw mechanism. So, as I said, new fields in this model bring new processes that are not present in the standard model. And the ones that I will be talking about are the baryon number violating processes. More precisely, the proton decay, which is the most prominent baryon number violating process in SO10, since it has no background coming from the, so it's not present in the standard model. The problem of most of the proton lifetime predictions in grand unified theories is that their theoretical uncertainties span over many orders of magnitude. So this is the common problem for these SO10 or these grand unified lifetime predictions. But what we aim in our study is to actually make very precise prediction of the proton decay, which will have a theoretical uncertainties at most 1 or 2 of magnitude. So we are actually lucky that we can do that, because only recently these hadronic matrix elements, which go into the proton lifetime prediction, are under control, or they allow us to do this prediction. Plus, only in this minimal renormalizable SO10 model, all other uncertainties that can change alpha gat or the Grand Unified mass are robust with respect to the theoretical uncertainties. So actually in this model, we are lucky then that it's even possible to do this precise or more precise prediction. So, so we want to make a proton lifetime calculation. So we created a kind of a proton decay cookbook. So it's a set of steps we want to do to actually get this proton decay lifetime prediction. So the first step one would start with is to identify your parameter space. So how many dimensions does your parameter space have in this model? So if you have a look at the scalar potential plus the gauge coupling, you will see that your parameter space has 17 dimensions when you exclude information from Yukawa sector. So you have quite big parameter space. But so now we want to take this parameter space and we want to look at it and constrain it using physical criteria. So let's proceed. So the first thing one want to think about is that we know only how to calculate in perturbative regime. So we want to kind of stay in this perturbative regime. So we would like to put some perturbativity constraints on this parameter space. And we wanted to make this criterion not that trivial, like we wanted to make more elaborated perturbativity constraints, meaning that we are handling one loop corrections, so we can use them. So we define this, let's say, vacuum stability perturbativity constraint where we compare or where we look at the 3-level vacuum and 1-loop vacuum and try to check if they are not too far from each other. And we check this feature for different normalization scales for which we use, like for learning, we use 1-loop beta functions. Plus, there is really interesting wave structure in the stationarity conditions, which kind of constrains all the waves, because if you don't want this dimensional full parameter to explode, you are actually forced to go into these 4 distinct cases. So you get more restriction also from this. Plus, we also compare the 1-loop corrections of scalar masses with the 3-level average masses, meaning that the maximal 1-loop scalar mass correction has to be smaller than the average 3-level mass. So these were more elaborated perturbativity constraints. Okay, let's proceed. So the next step is to check check or find the regions where not only your points are perturbative, but your points are also or have also non-tachyonic spectrum. So this is actually a very crucial requirement, because requirement of having non-tachyonic spectrum is really physical. And in this model, it actually gets even more complicated because you are forced to calculate 1-loop corrections of scalar masses, because the scalar spectrum actually contains accidentally light pseudo-Goldstone scalars. So you have to go beyond the 3-level calculations. And we calculated all full 1-loop effective scalar mass collections and incorporated it into these tachyonicity constraints. So it's not that easy to check tachyonicity just for 3-level, but we also have to calculate with 1-loop level calculations. Okay, let's go to the other step. So now we restrict ourselves to the perturbative regime, to the tachyonic, non-tachyonic spectrum. And now we want to extract gut scale, which actually sits in the proton lifetime prediction. But to have precise enough prediction, one has to go beyond only 1-loop gauge coupling running. One has to actually use 2-loop gauge coupling running to have actually chance to have a proton lifetime prediction with theoretical uncertainty smaller than this, or at least of the order of 1 order of magnitude. So we had to use two-loop gauge coupling unification, which is actually also like a useful criterion to narrow down this viable parameter space, because not all of the points will unify. So they have a typical scenario. This is actually one loop, and you can see that all of you need to have a unification of all the couplings usually in all the GATT theories. Okay, so what I described now were like more technical details, like a study of the parameter space and restricting it by all these criteria which were physically motivated. And this was actually what we were focusing on. So the next step, which we still have to work on, is to extract information from Yukawa sector and hadronic elements, and then really get the proton decay, but this is still to be worked on. So, so I will maybe do a summary. Okay, so I try to present you this minimal renormalizable non-supersymmetric SO10 theory, which contains in the scalar spectrum 45-dimensional representation, and then 126-dimensional representation, and then 10-dimensional scalar representation. We are actually lucky in this model that in this model, proton lifetime estimates are robust with respect to theoretical uncertainties. So in this model, we actually have a chance to make a proton lifetime prediction, which will have theoretical uncertainties smaller than 1 order of magnitude, which is not usually the case. And what we did so far is that we made a model analysis which involved the study of the parameter space, but this study was more elaborated because we also incorporated many considerations about perturbativity, like more elaborated considerations about perturbativity. We also had to check the non-tachyonicity of the spectrum, which also included one-loop scalar mass calculation. And on top of that, we want successful two-loop gauge unification. So these are all these steps that were put into.
Okay, thank you very much for a nice talk. Any questions? Okay, there is one question by Renato. Please unmute yourself. Go ahead.
Hi. In the two-loop gauge unification analysis, so do you have to include the Yukawa interactions?
So typically their contribution is really small. So if we are in this stage where we don't consider this information from Yukawa sector, basically, so their contribution to the running is so small that the mistake that we are making by not including them is really, really small. Plus, we have, even though if we don't have full information about Yukawa sector, we still have some information, which, for example, we have information about traces of these Yukawa matrices and so on, which is, I would say, enough.
Okay, thank you.
Thank you. More questions? If not, thank you, Katerina, again.
Thank you.
And we'll proceed to the next. Yeah, stop sharing, please. Proceed to the next talk. So next talk is Professor Anton Redhan. Please share your slides. Excellent. And yeah, if you can do the full screen. Doesn't work. If it doesn't work, we can just live with that. I think it looks fine. So if you can unmute yourself. Okay.
Oh, I'm unmuted. Somehow my control buttons disappeared when I went to full screen. So I don't know what's going on.
I think it is fine. I think it's actually fine. Yeah, we see your slides well. So yeah,
actually I see them twice. I have a full screen version and on top of it, the non-full screen version.
I see.
It's a bit weird.
Yeah, we see them just fine. So if it doesn't work, I think we can just proceed with that. Yeah, I think they are fine.
Well, maybe I can try again.
Yeah, well, let's try again.
So. I'm so sorry. No, this has disappeared completely. Okay. Okay. Does it look good now to you? Do you see my screen?
It's kind of similar as before. There is even one more thing on the left. We see our screen. Yeah, it's just that the slides are smaller.
Oh, I see it full screen now. This is incredible. Okay, well, I don't know what to do with that.
Yeah, if you can turn off these contents on the left.
Yeah.
Yeah. I think this is great. Yeah, so let's just start. Okay, so we are happy to have Professor Anton Rebhan from Vienna talking about axial vector transition form factors in holographic QCD. Please start.
Okay, thanks for having me, and sorry for the mess up of this slide. Yeah. The talk is quite, the title is quite a mouthful, so let me briefly explain what this is about. This is about one particular non-perturbative contribution to the standard model prediction for the anomalous magnetic moment of the muon, namely how axial vector mesons couple to photons. So transition form factors is about the electromagnetic properties of axial vector mesons. And holographic QCD is used for getting some information on the perturbative, this perturbative contribution, which is actually not well understood from other approaches. So how do I proceed? Now I have to scroll down. As you all certainly know, there's since 20 years a 3 to 4 sigma discrepancy between the theory and the experiment in the anomalous magnetic moment of the muon, which is now under experimental study by a new experiment. So the experimental result from about 20 years ago is about 3.8 sigma standard deviations below, above the standard model prediction. The new experiment is an attempt to improve both statistics and perhaps poorly understood systematic errors. There are quite nice talks at this conference about the technical difficulties in really pinning down this number, which I can recommend. So this talk is a theory talk. It's about one particular ingredient in the standard model prediction. This is the hadronic light-by-light contribution. There are actually two hadronic contributions which are poorly understood or not sufficiently understood. One is the hadronic vacuum polarization, and that appears in the effective one-loop diagram, and hadronic light-by-light scattering, which is a smaller contribution, but which is of equal importance, although its contribution is smaller, except that quite recently there has been some new doubts cast on the hadronic vacuum polarization, because new lattice results from the Wuppertal group, the so-called BMW collaboration, thinks that they can reduce the errors on the theory side or the lattice side so much that they are competitive with other evaluations, while not moving the central result before it had large error bars. And they are even claiming that the discrepancy between theory and experiment could be resolved by this. Well, this is some open issue that one should keep in mind. The conventional wisdom is that hadronic vacuum polarization is not explaining the discrepancy, and a large amount of effort has gone into pinning down hadronic light-by-light scattering, which has a number of theoretical uncertainties. Here I'm listing some previous results. You see all the results from phenomenological models. The LMD plus V is one particular phenomenological ansatz. And that result has changed over time by more refined approaches. Dispersive is a data-driven approach, which is almost considered the gold standard now. That has moved a little bit down. Lattice results are becoming available, and other approaches also point to slightly lower values. But all these results so far were confronted with one open question, namely that all this is related to the axial anomaly, and Melnikov and Weinstein have pointed out that the non-renormalization theorem for the axial anomaly makes it clear that all the standard hadronic modeling of the hadronic light-by-light scattering, which you see in this diagram, suffers from a discrepancy with the short distance constraints, which I will call Melnikov-Weinstein's short distance constraints. So that was pointed out already in 2004. And back then, they have estimated the possible effect of the necessary corrections to satisfy the short distance constraints in a simple model they've come up with, which is a bit controversial, where an extra contribution, which is quite sizable compared to the errors that you see here, and which would be even larger with modern input data. So this would be going quite a bit towards diminishing the discrepancy between theory and experiment. And what I'm going to talk about is new results using holographic QCD that will shed light on this issue. And in particular, I'm going to quickly review hadronic holographic QCD results on the pion contribution, the so-called pion pole contribution, which also involves a non-perturbative transition form factor, which is called capital F. There's previous work which has studied holographic QCD predictions for this, but it's interesting to revisit that because there's newer low energy data which we can compare with. And then the main theme of this talk is actually a new calculation of the axial vector meson contribution, which can also be exchanged in this light-by-light scattering amplitude diagram. So the pion has couplings to two photons through the axial anomaly, and so has the axial vector meson. This is less well understood because there is less experimental data. And theoretically, it's also not well understood, and it was pointed out by Melnikov and Weinstein that axial vector mesons actually play a crucial role in resolving the fundamental issues with the short distance behavior here. And what I'm going to present is work together with Josef Leutgeb, where we have done some calculations in a couple of holographic QCD models, predicting their contribution, and particularly in view of the Melnikov-Weinstein constraint. So let me quickly introduce what holographic QCD brings in. Holographic QCD is a possible window to strong coupling physics by extending the famous ADS-CFT correspondence of Maldacena to non-conformal situations and using it as not in the highly supersymmetric case, but in the non-supersymmetric, non-conformal invariant case of real QCD. It's a five-dimensional theory in this modeling, which can be either some bottom-up construction, which is purely phenomenological, or it could also be string theory motivated, and they're the best known model that goes some way towards a dual of large N QCDs, the so-called Sakai-Tsukamoto model. And I'm going to discuss all these models together because in the end, they boil down to a certain five-dimensional action for Young-Mills fields, where the Young-Mills fields are the duals of the vector mesons and axial vector mesons, and they also contain in them, as so to say, as the fifth component, the pseudoscalar mesons. So one has a fifth coordinate. Z equal to 0 is the conformal boundary where the ultraviolet theory lives, and then non-zero Z goes to lower scales, to the infrared, which is in these holographic models, in the bottom-up models, cut off in either a smooth or sharp way, which is then called hard wall or soft wall models. So in the soft wall models, one actually has an infinite range for the set zero, but one is actually deforming the geometry away from ante de sitter and therefore breaking conformal invariance. The top-down model is not asymptotically ADS 5 to begin with. It's anyway just a model for low energy scales. But the Sakai-Tsukamoto model was a particularly nice model of introducing a geometric representation of chiral symmetry breaking, which in the bottom-up models can be either introduced in a way by introducing extra bifundamental scalar fields which do a symmetry breaking, or in what is called hardwall 2 model in the following, the so-called Hearn-Sans model. It's through different boundary conditions for vector and axial vector fields. This is actually a mechanism which is then rather similar to what the Sakai-Tsukamoto model automatically does with the branch construction. Now, our interest is in transition form factors that have to do with the axial anomaly. And the nice thing is that the axial, all the flavor anomalies are nicely represented by the Westermüller-Witten term, which originally was already a 5-dimensional thing, which now finds a true 5-dimensional setting. It's derived in the Sakai-Tsukamoto model. There it automatically comes with Dirichlet branes that one introduces for chiral quarks. And in the bottom-up models, it's introduced by hand simply, adjusting the prefactor so that one has the correct axial anomaly. As I said, in the Sakai-Tsukamoto model, that is already provided by the whole construction. Now, we want to also see electromagnetic couplings as usually in chiral perturbation theory. This can be done through the vector fields in the holographic setting. The modes of the vector fields describe mesons. These are normalizable modes. But electromagnetic background fields can be introduced through non-normalizable modes of the vector fields. One could also introduce background axial vector fields, but this is of no interest. We want to have conserved electromagnetic fields describing photons. And this can be done by simply introducing the charge matrix in flavor space and insert electromagnetic background fields in this way. In the holographic setting, this then introduces a so-called vector bulk boundary propagator. I have no time to explain the details. I just want to show some expressions in the hard wall models. This is given by Bessel functions. In the soft wall model, this can be also given in closed form by so-called hypergeometric U function or trichome function. In the Sakai-Tsukamoto model, it's a bit more complicated and not, well, not complicated. It simply cannot be given in closed form. One has to do it numerically. And the nice thing is that the Chern-Simons action then automatically fixes everything of the coupling of the pion, whose wave function is given here, through two bulk boundary propagators, which then give the coupling to photons, and Q1 and Q2 are the virtual momenta of the photon when the photons are virtual photons. There's a slight technicality that has been pointed out in this paper, the hardwall 1 model, where one has a sharp cutoff in the infrared. Actually, there's an extra boundary term appearing in the Chern-Simons action, which has to be dropped for consistency. Now, if one is now inspecting what this gives, one can calculate, for instance, the asymptotic behavior. In the bottom-up models, the asymptotic behavior is given by the ADS5 geometry. Well, it's either completely ADS5 in the hard wall models or asymptotically. And then one obtains this closed form for the transition form factor. And amazingly, the resulting structure, which depends on these two virtualities of the photons, has precisely the form that was worked out by Brodsky and Lepage in perturbative QCD. So this is reproducing the correct form, and in one of the hard wall models, even the numerically exact form of the asymptotic limit. The hard wall 2 model has a prefactor that is 62% of the leading order perturbative QCD results, so it's not fully saturating the short distance constraint, whereas the Sakai-Tsukamoto model is a model which is only valid in the low energy limit that has a different fall off. It's not consistent with perturbative QCD, but nevertheless, it has a symmetry dependence, which is qualitative, roughly, if you plot the function, has a similar form as this logarithmic function above. Now, comparing the result not asymptotically, but in the infrared, where we need the contributions to calculate contributions to G-2. Here we can compare with recent experiments. There's a recent addition from the BES3 experiment. And it turns out that all these bottom-up models, these are the upper 3 colored lines, are just on top of the experimental data for single virtual transition form factors. The Sakai-Tsukamoto model, which is only valid in the infrared, has the correct slope in the infrared, but then decays too fast. Now, this is also obtained correctly in simple phenomenological models, but the new thing is that this model offers a convincing continuation to the double virtual case. And inserting that in a two-loop diagram and calculating it, it turns out that the holographic QCD predictions are quite consistent with the recent lower values that was obtaining, so lower than the old phenomenological models. Now, I have to speed up a little bit. Coming to the axial vector mesons, we can do the same because one and the same expression, namely the Wessel-Minowitten action, was giving at the same time the pseudoscalar couplings to photons and also the axial vector mesons. So this is now written out in a 5-dimensional form for the coupling of photons represented by these curly B's to the axial vector mesons. And it turns out if one is looking at this expression, this is automatically respecting the Landau-Yang theorem, which says that axial vector mesons cannot decay into two real photons. At least one of them has to be virtual. This is explained here. Now going to the actual evaluation, it turns out that the amplitude one has for axial vector mesons when they couple to photons is a slightly more complicated form than has been used before in simple phenomenological models. It turns out to be an asymmetric transition form factor, which is represented in terms of this spike to boundary propagator here. Unfortunately, experimentally, one only has information on the case where only one virtuality is non-zero. There's just one experiment, the L3 experiment, where one has a bit more information. That gives the normalization of this transition form factor, which comes out at 15 Jeff squared, inverse Jeff squared. And it turns out that the holographic QCD results are roughly in the right ballpark. They're slightly too high. The Sakai-Sakamoto model is actually closer. And if one now looks at the dependence on the virtualities, this is a comparison of the experimental results. The experimental band is given by the gray band. And the two hard-wall models that I'm going to consider further are almost on top. This is the red and orange line. You see that they're in completely consistent with the experimental result. Even the Sakai-Sakamoto model, which eventually falls off too quickly, is quite in agreement with the experimental results. Now going to the double virtual case, which is of importance in the evaluation of the G-2 diagram. Here we get these colored lines, and here I'm just comparing with what simple extrapolations have been done in the past. So previously simple dipole models were traditionally used for calculating the contribution to the anomalous magnetic moment. And here one does see a discrepancy between simple phenomenological models and what the more refined holographic model is providing. Now, coming to the theoretically most important aspect of all this is the Melnikov-Weinstein constraint. Melnikov and Weinstein observed that a particular limit of the for photon amplitude, one particular component which is given here, has this limit which is non-vanishing when the virtuality Q, that is the virtualities of these photons, is sent to infinity first, where the third virtuality is sent to infinity last. It has a non-zero result, which is given by the axial anomaly. However, all the simple models that have been used for describing meson exchanges actually give zero in this limit. And what Melnikov and Weinstein have pointed out, one could repair this simply by replacing in this diagram by dropping one of the transition form factors in this diagram. That is then leading to a drastic increase of the whole contribution, around 40%. And this was actually the model proposed by Melnikov and Weinstein. Now, quite recently, the group of Colangelo et al. Have pointed out that the deficiency comes from well, one possibility to cure this deficiency is to include an infinite tower of exchanges in this diagram. And they considered a Regge model for an infinite tower of pseudoscalar mesons and came up with this estimate. Now, in the holographic QCD model, the nice thing is we automatically have an infinite tower of axial vector mesons. And this infinite sum of the infinitely many axial vector mesons reads like this. And inspecting this expression, one indeed finds that every single contribution in this infinite sum has a vanishing limit if you go to virtualities to infinity. But if you carry out the infinite sum and take the limit afterwards, as you should, then the exact result of 2/3 required by the Melnikov-Weinstein constraint comes about. And one of the models where the overall factor of the short distance constraints is in agreement with perturbative QCD, the Melnikov-Weinstein short distance constraint can be satisfied exactly. The other model satisfies it qualitatively with at the 62% level, which is perhaps not such a bad feature that it is below it, because in real QCD one has next to leading order corrections which bring the result down. In the top-down model, the fall-off is too high, too fast. So here the short distance constraint is not satisfied. Now, let me show how this comes about, that each contribution gives zeroed to this limit, whereas the infinite sum gives the required result. You see the individual contributions peak at the scale of the axial vector meson masses and then drop off. And if you have an infinite tower of more and more massive vector mesons, the individual contributions peak at higher and higher values, and the complete sum of the infinite tower gives them the required approach to the short distance constraint. So here, then the numerical results, when we plug in the results to the formula for the two-loop formula for the G-2 anomaly called mu. And here one sees that the first, the lowest lying axial vector meson is actually giving the largest contribution. The others are giving small, but still non-negligible contributions. So 3/4 approximately is provided by the lowest axial vector mesons, and then the complete result is somewhat higher. Summing up everything, the pseudoscale and the axial vector meson contributions, this is what the two models that we considered give. It's interesting to compare with this controversial Melnikov-Weinstein model. There, the longitudinal contribution was around 4.10 to the minus 10. Well, here the blue corresponds to this result. It's smaller than this large result, but in total, the axial vector meson contribution is of the same order of what this model was giving. I should also say that 3 days after our paper, the group of Capiello, Carter, D'Ambrosi, again, and Ayer were doing almost exactly the same and sort of analysis, but just using the one of the models we considered in a different way with different set of parameters. So they were also bracketing essentially the short distance constraints by doing so, and their results are compatible with ours. So I have to come to an end. Let me skip perhaps this extrapolation and immediately come to the conclusion. The conclusion is that holographic QCD, even the simple models that holographic QCD provides, allow for analysis of what's going on with the axial anomaly and how the short distance constraint of Melnikov-Weinstein can be saturated. The result then points to a sizable contribution of axial vector mesons, which is interesting because previous estimates have disagreed quite a bit among themselves, but come up with results that are significantly lower than what this holographic QCD model suggests. Well, in the end, we come up with a prediction of a slight increase of the hadronic light by light contribution, but it is still telling us that hadronic light by light is under control. It's not removing the 3 sigma discrepancy between theory and the experiment. So I have to stop here, I'm afraid.
Okay, thank you very much for an interesting talk. Any questions? Okay, I don't see any questions. Thanks, Professor Ebhan, again.
Thank you. I used up my discussion time anyway.
Yeah. Yeah, so please stop sharing your slides and we will move to the next speaker. Thank you. Next speaker is Pablo Pais. Can you please share your slides?
Yes, I will try. Can you hear me?
Yes, yeah, we can hear you
Okay.
well. You can also turn on your camera.
It is sharing?
It's still working. Yeah, yeah. It's now sharing.
Okay.
Your camera is still off.
Yes, sure. Sorry. Let me see if I can turn on it.
Okay, good.
Okay.
Yeah, just the screen kind of froze.
Yes, I don't know. I'm waiting. Perhaps my computer is very slowly, so let's see if, because my screen is in dark now. So
yeah, we also see dark.
let's wait. Now, is this okay?
Yeah, yeah.
Okay, thanks.
Okay, so let's continue. So Pablo Pais will talk about the torsion through time loops on bidimensional Dirac materials. Please.
Okay, thank you for giving the opportunity to talk about this work, which was made with Marcelo Chapina, is a researcher at ICHEP Barcelona. Alfredo Giorgio is a professor at IPMP at Charles University, and Adamante Zampelli is a former postdoc from Institute of Theoretical Physics, also at Charles University. First of all, let me say that this work, which was published this year in PRD, is part of a bigger project trying to use graphene, or more precisely graphene-like materials, to trying to reach with graphene-like material, try to use graphene-like material as a tabletop lab to trying to reach what is unreachable by direct experiments or direct astrophysical observation of different theories of high energy physics. One of the prototype of this goal, which was started, this kind of project using graphene as a tabletop lab, was started by Alfredo Giorgio, by Professor Alfredo Giorgio almost 10 years ago. One of the goals they reached with this team was to, for instance, use graphene to trying to measure some kind of footprint of Hawking radiation. And in the case of this work, we are trying to reach other thing which until now is unreachable, which is torsion. Torsion is an intrinsic property of space-time. We still don't know if torsion play an important role in gravity or gravitational theory. For instance, there are models which let's say, include torsion in a minimal scheme. This is, for instance, the case of Einstein-Cartan theory of gravity, in which torsion is included, let's say, in a minimal coupling way. So let's try to see if we claim that with graphene, perhaps we can reach this part of the space-time, in this intrinsic property of space-time. Of course, in an analogous system, as it's graphene is not a direct experiment. So what I would like to explain in the first slides is the properties which are useful for us to use a graphene as a tabletop lab. First of all, graphene, as you know, is made of carbon atoms. It's a bidimensional. It's made of this typical bidimensional honeycomb shape. Actually, there is made of two intertwined triangular sublattice. Here is represented by these green dots and white and yellow dots. Sorry. One of the peculiarities of graphene is that you need two of graphene, or the honeycomb, let's say, of the honeycomb, this honeycomb lattice. You need two set of vectors in order to span the carbon atoms instead of only one, as for instance the square lattice. The carbon atoms has four electrons allowed to form covalent bonds. Three of them makes covalent bond with one of his neighbors. These are the sigma bonds, and these electrons are called sigma electrons, which is a very strong bond. This is why graphene is one of the strong material ever made. And these electrons are responsible for the mechanical properties or elastic properties of graphene. The fourth electron allowed to make bonds makes a weaker bond, as a pi bond, which is much, as said before, is much weaker, and therefore these electrons can hop between different carbon atoms. These are called pi electrons, and these electrons are responsible for the electronic properties, or one of the are responsible for the appealing electronic properties of graphene. So let's, just to fix notation, or just to fix convention, let's say, here is shown why, here is shown our election of these two sets of vectors. The first set is the vectors A1 and A2, the vector A, which goes from sublattice A to another side of sublattice A, going from black dots to other black dots in this picture, is representative of lattice sub of the sublattice A, sorry. And then you have the second set of vectors. These are three vectors, S1, S2, and S3, going from this black dot to a white dots. The white dots are representative of the sublattice B. L is the distance, around 1.444 Armstrong, the distance between near neighbors. Is the lattice distance, let's say, the minimal lattice distance. So taking the time binding approach, the time binding approach is, in this approach of time binding, you assume that the electrons are very localized around the carbon atoms. And if you take only near neighbors contribution, you can expand the Hamiltonian in these ladder operators A and B corresponding to sublattice A and B. These are these anti-commuting operators. And you can see that in order to expand the Hamiltonian, you need this, because you need two sets of lattice. You have two sums, the first one going between, for instance, in this case, lattice A, and the other goes through the three vectors of the near neighbor vectors of the base S. Eta is a parameter, is the, let's say, the Hoping energy, is around 2.8 eV, is the energy you need that the electron hopping between different carbon atoms. The pi electron. This is to describe the pi electrons, right? So if you go to the Fourier space, make the Fourier transformation, you get this result, and appearing this result is this very important function, which whose zeros are where the electronic and conductivity band touch each other. In the case of graphene, these are localized at points in the Fourier space. Actually, there are twin equivalents of that point because of the symmetries in the Brunel zone. These points are called Dirac points. We've seen a moment why they're called Dirac points. These are, in our convention, these 2 points. And if you rearrange, let's say, the ladder operators A and B in this form, with psi, defining this psi plus and minus, and then you get this Hamiltonian, which you can recognize as the Hamiltonian in the Fourier space of expanding around one of the Dirac points. You get this Hamiltonian, which is the Fourier space Hamiltonian of massless Dirac Lagrange, the Hamiltonian obtained for a massless Dirac Lagrange. This is why they are called these Dirac materials or wall materials, because are massless. So the effective description of these pi electrons with all this approximation we made can be represented by this Hamiltonian. For instance, in the dispersion relation, taking into account near neighbors, has this form of this egg box form. Here, this surface is only the conductivity band surface, the conductive band surface. Let's say the covalence band is in the opposite part of the plane, in the down plane. But if you expand, this means that you obtain this cone, which is called the Dirac cone, because the slope of the cone is, instead of being the speed of light, is the Fermi velocity, which is the velocity of the electrons moving in the graphene, the conducting electron, the pi electron moving in graphene, which is around 1,000 kilometers per second. Is, let's say, 300 lesser than the speed of light. It's a very high speed for materials. This is one of the appealing properties I said before of graphene, of the pi electrons in graphene. So the main message here is that in all these approximations, you can describe the pi electrons by the massless Dirac Hamiltonian around these Dirac points. Okay, this works very well for a pristine material, or let's say a graphene without any strain or any defect. There are, let me say just before continuing, that there are other materials than graphene. This is why we call in the talk Dirac materials. All the materials that have this property that around one of the Dirac points has the description, has this massless description of the Hamiltonian. All this material, I call it Dirac material, graphene-like material. Nowadays, there are more materials than graphene, like silicene or germanium, for instance. So from now on, all what I will say could also be applied for those materials, more general materials, graphene and graphene-like material, this bigger family of materials. So suppose now I will describe one type of topological defects which are present when you synthesize graphene, which is called disclination. Suppose you have this graphene sheet and you cut this triangle and remove this triangle, and then finally you identify these semi-lines here, and then you get, this is called the Volterra process, and you get these pentagons surrounded by hexagons. If you could see this in a three-dimensional space, you see that this has the form of a cone. Actually, these materials are called, or this result of the Volterra process are called nanocones, and has different properties, electronic properties of graphene, because this topological defect has significant effects on the the behavior of the pi electrons. Even more important than the defect itself, which is called is a topological defect in the sense that this defect cannot be removed by smooth deformations. You have to glue and you have to cut, and you have to cut and then to glue. This is why it's topological. The defect is topological. More important, as I said before, more important than the defect itself is the distribution of defects. You can have many of these defects, but if they are distributed in very particular way, you can get in the continuous limits some signature of curvature. For instance, if you put 12 of these pentagons distributed in very particular way, you get something similar of this buckyball. In that case, you can see that the black patches are pentagons, the white patches are hexagons, and this buckyball actually is like the prototype of what is called fuellering. And you can see that this in the continuous limit, if you have even more and more atoms, but every time 12 pentagons, you can get a more and more surface closer to the sphere. So you can see that going from the lattice from a topological defect, which in this case is disclination, you can go to the continuous limit to something which has, in this case, positive constant curvature as a sphere, right? If instead of removing this triangle and gluing, you cut and you insert another triangle and glue, you have again a topological defect. Also, it's called disclination. This time, because of convection, has a negative angle of excess angle. And instead of have a nanocone, or instead of have a cone shape in 3D, you can see that this in 3D is more like a saddle. And again, if in this case, if you introduce different heptagons in different regions along with pentagons, you can get something like that, which is, you can see, is the form of a trumpet. This is called the Beltrami surface. It's a surface of constant negative curvature instead of positive. And this picture is taken from this paper. This paper is the leader team of Alfredo Giorgio. They made in this paper, this is a computing simulation. It's still not synthesized in the lab, but at least in this paper they showed that this is a stable macromolecule. It's a stable macromolecule. You can see the details in this paper, led by Alfredo Giorgio. Okay. Now let's go to the other important defect which concern us in this work is dislocation. Suppose you have two disclination in this way, making an heptagon and pentagon. This is equivalent to cut this half plane and introduce a strip on them and glue. Again, this is why it's also a topological defect. And the distance that the length of the strip you introduce is called, this is in this case, in this defect is the Berger vector. And this effect as a whole is a dislocation. This is a particular dislocation. It's called edge dislocation. It's a 2D dislocation. There are other dislocations in 3D, like a screw dislocation. And in particular, this heptagon-pentagon dislocation is called also glide dislocation in the jargon. So as much as in the case of disclination in the lattice through the Volterra process, and you go to the continuous, you can get this something in the continuous limit of positive or negative curvature. You can get with this kind of defect to the continuous limit to something related with torsion. And this is very well known from the gauge approach to defects, to topological defects. This is showed in this classical book of Kleiner, that the vector, the Barger vector, sorry, is related through this formula to the torsion. Somehow torsion, let's say, is the surface density of Barger vector. This is not an easy formula, but at least you know that a non-zero, Barger vector implies a non-zero torsion in the continuous limit. So with this in mind, let's point one of the properties I would like to say about torsion, as intrinsic property of torsion, of the intrinsic geometry property of a space-time or a space in general. Suppose you have two vectors and you're trying to have a parallel transport of the first vector along the second one, and then again, and you get this vector, and then you parallel transport the second one along the first one, and you get the other vector. If you fail in closing this parallelogram, then this is a signal that your space has torsion, intrinsic torsion. It's intrinsic in the sense that you don't need to use some embedding space to reproduce this. It's an intrinsic property of it's an intrinsic property of the space. And what is important for us is that torsion has 3 index. It's a tensor which has 3 index. 2 index related to this to the direction of these two vectors, and the 3rd index is related where the non-closing parallelogram direction points out, let's say. So this is why you need 3 indices for the torsion tensor. And it happens that when you, at least in the minimal coupling, you minimal coupling torsion with the fermions, this coupling only survives the total antisymmetric part of torsion. So this is why appears this Levi-Civita tensor in torsion through a coupling with torsion and the fermions. So it was realized by the group of Maria Bosch-Mediano in Madrid 10 years ago that in two-dimensional materials, because torsion have 3 index, it's a tensor with 3 index, and if the total antisymmetric part survives, you need at least 3 dimensions, 3 different dimensions to get something different from 0. And they conclude in this paper that at least for two-dimensional materials, it's very difficult to spot torsion, like in graphene or graphene-like materials. They say that in third-dimensional materials with 3 dimensions, this can be done, but not in two-dimensional materials as torsion. But our bets here, and this is our contribution in this work, what happened if because we do have a 3rd dimension in the game, which is time. Even more for the Lagrangian formalists, time is very natural dimension to start with. So if we have the possibility to include time, we do have the possibility to get something different from 0. And this can be done in 2 ways. Let me go back to this picture. For instance, it could be the case that the non-closing direction, the non-closing direction of the parallelogram could be time-like. This is pointing out to what is called time crystal. It's a very interesting path to follow, but we didn't follow this path. The other path we can follow is that one of these 2 vectors could be time-like, and the non-closing parallelogram is space-like. And this is pointing out to what we call time loop. And in the next 2 slides, let me show you how we can figure out this in the lattice point of view. Suppose you have in the lattice, through some external field, you allow that electron, not electron, let's call this particle, going back through the y-axis, through, let's say before, some external electromagnetic field, some external field, let's say. And the hole which is the vacancy of these electrons, going back in the opposite direction. This is in the in the XY plane. But if you go to the YT plane, it's like the particle going back. So they make this trajectory, and let's say the hole make the other trajectory in the opposite direction, as I said before. But in the YT plane is made in this trajectory. Of course, this is just a sketch. Let's say, doesn't to be necessary to be a circle. Could be some mass, a sinusoidal or whatever. It depends on the standard field you put, of course. But let's say in the quantum field theory description, the holes, which are the representative of antiparticles, can be thinking as particles going back in time. So this particle hole view could be equivalent to this particle view, that is a particle making this loop in the YT plane. This is what we call time loop, because time is included in the surface where the loop is done. So this is for the pristine material without defect. Now suppose we introduce a Barger vector, let's say, or we introduce a dislocation, let's say, and we know that dislocation, non-zero dislocation, is related to a non-zero torsion, in the continued limit. So suppose we introduce a magnetic field, a standard magnetic field, in order that the particles follow this path. The hole will hold this other path, but this hole will, let's say, will face this Barger vector, or let's face this abstraction. So the path will be changed, and therefore the looping is not closing. Very similar to the parallelogram picture I showed before. So this is our bet that the Barger vector, or in the continuous limit torsion, has observable effects. This is our bet in this paper. In the paper, we let's say we go 2 or 3 steps ahead of this. We have a candidate for the observable. We suspect that is a current. Let's say there is some kind of current in which take into account this non-closing loop. Other challenge here is going from this lattice to the continuous limit. It still is not clear if the correspondence between some particular configuration corresponds some particular torsion tension or many, or vice versa, if one particular torsion tensor corresponds to many different configurations in the lattice limit. We still don't know it. We have to polish up all this. And once all this issue is solved, let's say, of course, our goal is to make a setup or an experiment for doing that. So thank you very much. Of course, I will be happy to answer your question, and also in the discussion room. Thank you.
Thank you for an interesting talk. Are there any questions for Pablo?
Mm-hmm.
Please raise your hand if you have any question. Okay, I don't see any questions, so thanks, Pablo, again. And we will now have a 15-minute break, and we will reconvene at 6:50. Thank you.
Thank you.
Okay, it's 6:50, so we can continue now formal theory development session. So I would like to ask the next speaker to share the slides.
Yes, here I am.
Mm-hmm. Hello.
Can you see that?
Yes, excellent. Yeah. Okay, so let's start. So the next speaker is Antonio Costantini, and he will talk about the scalar potential of the 331 model theoretical constraints. Please start.
Okay, thanks a lot. And before starting, let me thank the organizer for the opportunity to present this work at ICHEP. And as the title said, I will discuss about the scalar potential of the 331 model, and in particular, the theoretical constraint on this scalar potential. So this work is based on a paper with that I wrote together with Margherita Ghezzi and Marco Pruna back in January, actually, but by chance the paper was published in PLB just today. So you can see all the links here if you are interested. So it's almost dinner time, so let's look at our menu. I will start with some very basic old-fashioned stuff on the Higgs in the SM, in particular the unitarity constraint that will follow from WW amplitude, just because it will be an ingredient of our work, and it's useful to see what is the difference between the standard model and a BSM model in terms of direct calculation. And then I will discuss some general features of the 331 model. Let's say I will present you what are the field content and the most relevant ingredients that we studied. And in the second and third part, I will present you the main results of our analysis that are the unitarity constraint, the analytical unitarity constraint on the 331 model. And in the end, we also analyzed the boundedness from below for the scalar potential. So, but let's start from the beginning. So the unitarity constraint in the standard model, I will of course go very quick on that because it's a textbook scenario. So we know that the mass of the Higgs boson in the standard model can be constrained by the unitarity of the standard model itself, meaning that the WW scattering will of course be constrained by the presence of the Higgs boson, and the mass of the Higgs boson itself should not be greater than a certain value in order to have unitarity. So it's a very well-known story. One can compute the amplitude, in particular in the very high energetic limit, where the center of mass energy is much larger than the W mass, and you get this quite simple expression. Then the general strategy is to write the amplitude as a sum of partial waves, and in particular, one can write even the cross section as the sum of these amplitudes. And then by the optical theorem, it's well known that each of the coefficient AL must be at most 1/4 in order to have in order for unitarity to be preserved. So the constraint on the Higgs mass that one can extract from the planar wave, so from A0, is that the Higgs boson should be at most 870 GeV in mass. Actually, one can find even a stronger constraint on the Higgs mass itself, if you consider that from the equivalence theorem, you actually have to consider the boson amplitude, so the 2-to-2 bosonic amplitudes that in this case, in the case of the standard model, are given by W, Z, and H in all the possible combinations. So you will write basically a matrix with WW, ZZ, HH, ZH, WH, and WZ bosons. And from this matrix of the scattering amplitude, exactly in the same way as you did for, as one can do for the WW scattering itself, you will find that the highest eigenvalue must be lower than 1/2 actually. This is the standard constraint. And from this analysis, one can obtain that the Higgs mass should be lower than 700 GeV roughly. So we all know that the Higgs mass itself is much lighter than 700 GeV, and this means, for example, that the unitarity of the standard model has been experimentally proven. So one, of course, can ask, okay, why we have to go for beyond standard model physics? And here is a small list of reasons. You can look for explanation of dark matter, neutrino masses, electroweak phase transition, the hierarchy problem, whatever you want. One of the most interesting, and I will came back in a minute on that, is why in the standard model you have an equal number of quark families and lepton families, and these families are actually 3. And of course, there is the hierarchy in the Fermion masses and many other open problems, which may call for BSM physics. So let's consider a particular model, a particular BSM model, or to be more precise, a class of models. So the 331 model is actually, as I'm going to show in a minute, is a class of model with, with extended gauge symmetry. So in particular, the gauge symmetry of the standard model is extended in a non-trivial way. So the SU2 gauge group of the left-handed symmetry is promoted to be an SU3 group. And this, of course, will imply that even the U1, the hypercharge of the standard model, should be extended in some way. So this U1 that you see here is not, of course, the standard model hypercharge, but it is an extra U1 group. So why this 331 model? The name, of course, came from the rank of the groups. Why it is actually a class of model. So SU3, as we know, has 2 diagonal generators. And this means that one can, in general, construct the operator of the electromagnetic charge by combining the T3, T8, and the X, basically, generator. And in this linear combination, one can generally include a parameter which is called beta Q, which will give us the possibility to have different phenomenology with the same gauge structure, and in particular, you can have different electric charges for the particle of the model. I will show you how this happens. So, what is the field content of the model? You have the fields, of course, are arranged in triplet, because the fundamental representation of SU3 is the triplet representation. So here you have the first 2 family of quarks and the third family, which are treated differently. The reason for this different treatment will be clear in the next slide. And one can see in particular that the first 2 families lies in the fundamental representation of SU3, whereas the third family, the top quark family, basically, lies in the anti-fundamental. As you can see, the lowest component of the triplet here is an extra fermion state, is an extra quark state. So the model has, of course, extended gauge groups, gauge group, and even extended field content, matter and gauge field content. So the leptons instead are treated democratically. So they all belong to the fundamental, anti-fundamental representation of SU3. Again, I will explain the reason for this different treatment in a moment. And of course, for the sake of brevity, I've not put here the right-handed counterpart of these triplet fields, but you will of course have a right-handed fermion for each fermion of the triplet. So the right-handed quarks, the right-handed leptons, and the right-handed extra quarks and extra leptons. What about the scalar sector, which will be the fundamental ingredient of our work? So the scalars in the 331 model are again arranged in triplets of SU3. And you can see that we have labeled in general with A, B, 0, and plus minus, of course, the electric charge of the component of each field. So these charges QA and QB will depend, as I said before, on the parameter beta Q, which is responsible for the electric charge of each particle, and in particular for define it for a given selection of beta Q, you will have different electric charges for the fields. I will not go into the detail of the possible values of beta Q, but I can tell you that basically you can have a finite number of possibilities, because you will of course have the quantization of the electric charge, and moreover the constraint on beta Q will come from the expression of the extra Z prime mass, which is present even in this model, of course. So coming back to the reason why you have different treatment for quark families, and to the reason why you have 3 families of quarks and 3 families of leptons, in the 331 model, these constraints come from the anomaly cancellation. Here I just put the example of the SU3 cube case, because it's the most clear, but the same argument will hold for all the possible anomalies triangles. So by the assignment, by the charge assignment, you can easily see that you have a balance between the number of color and the number of fermion, a number of lepton families, which forces actually the quark and the leptons to be in a multiple of 3. So in the 331 model, you cannot have freedom from this point of view. Of course, this will not fix the total number of fields, but then if you think of the SU3 color running, so the running of the color gauge coupling, then you will understand easily that only kappa equal to 1 is actually allowed. Otherwise, you will not have the asymptotic freedom. So in a sense, the 331 model, so this class of models will force the number of lepton families and the number of quark families to be equal, and to be equal to 3. So this is something interesting, because in the standard model, of course, this is not explained in any ways. So let's have a look on the electroweak symmetry breaking in this model. Of course, when you think of extended gauge groups, you will have in mind that the electroweak symmetry breaking will proceed in many steps. So in this case, we will have a first breaking from SU2 cross U1, SU3 cross U1, sorry, to SU2 cross U1, given by the vacuum expectation value of the scalar that we call chi. And after that, you will arrive to the U1 electromagnetic symmetry, which is the symmetry that remains below the electroweak scale. After eta and rho, of course, the neutral component of eta and rho will take a VEV. From the gauge boson point of view, we can see that in the complete unbroken phase, we will have 8 gauge bosons coming from SU3 and the BX field coming from the U1. And after the first breaking driven by chi, we will have a Z prime, a pair of vectors with charge A and B, and then the usual gauge bosons of the standard model, which in the end will turn out to be the Z, the W, again the Z prime, and the Y and V gauge bosons. And of course, the photon is the only one that will remain massless. So the electroweak symmetry breaking is actually closely related to the scalar potential, because the scalars will, of course, drive the symmetry breaking. So the scalar potential of the 331 model is given in this big formula. And one interesting thing is that it is, of course, beta Q invariant. So you will construct the singlets out of the triplet field. And this means that this potential will hold for any choice of beta Q. It is actually not completely true that all the possible choices of beta Q will have this potential, because for one of them, you can construct more invariant because some of the representation will become equivalent. But these are something that we have not considered in our analysis. Of course, we have the masses, the mass parameters Mi. The F rho eta chi is the mass squared, sorry. F rho eta chi is a mass parameter, and the lambda and zeta couplings are dimensionless parameters. And they will be basically the ingredients for the analysis of unitarity and boundedness from below. But we will come in a moment. So what about the scalar spectrum? The scalar spectrum will consist into 3 neutral scalars, of course. We will have only one neutral pseudoscalar because we have a Z and a Z prime, so we will have 2 Goldstone bosons. Then we have one massive singly charged states because we have, as you can see, rho plus and eta minus. A combination of them will give the Goldstone boson, and the same is true for the A charged and B charged states. So in total, we have 6 massive scalar state, charged and neutral. So in general, what is done in the multi-Higgs model is at some point to consider the diagonalization of the various mass matrices, which means that one try to express the physical masses of the scalar Higgses, the pseudoscalar, the quark, the charged scalars, in terms of the parameter of the potential. So and the VEVs, of course. So the lambda, zeta, F rho, eta chi, and the various VEV in our model. We decided to consider somehow the opposite choice. So we try to look for the inverse diagonalization, which means that we actually succeed in that. We were able to express the parameters in the potential in terms of physical masses of the scalars, physical masses of the pseudoscalar, physical masses of the charged scalars, the VEV, of course, and the mixing angle. One important point is that in this scheme, the mixing angles should be considered as input parameters. So in general, one try also to express the mixing in terms of the masses, but in this inverse diagonalization procedure, these are actually some input parameters. So you decide that the scalars will mix in a definite way, and you will get the expression for the lambda, for the zeta in terms of these masses and rotation angles. And of course, you can try to see if your choice of the scalar of the spectrum will be consistent with unitarity constraint, boundedness from below, and all the Higgs constraint that you can try to impose. So this is in a word what we try to do. So here I present you an explicit example of the trading that we were able to perform. So here you can see that the lambdas, and the zeta are expressed in terms of the physical masses, the rotation angles, of course, and for the sake of clarity, even if the formulas are already cumbersome enough, these are expanded in terms of mass over Vk. So these are the first order correction in a sense. Of course, in our paper, we were able to give the full expression of the lambdas in terms of the physical spectrum. One interesting thing that you may note, looking, for example, at zeta 1, 2, is that you should have a certain degeneracy among masses if you want that your couplings, these are dimensionless couplings, so they have to be perturbative in a sense that they have to be at least lower than 4 pi. So you cannot have all the splitting that you want, for example, between MH plus minus 2 and the MA1, and MA1. Otherwise, this contribution will be much higher, of course, than V, which is the electroweak scale. And for example, your zeta 1, 2 parameter will become non-perturbative. Something similar, even if it's not really obvious, will hold for basically all the dimensionless coupling. So your scalar spectrum basically have to come with certain degeneracy. You can play with the scale between the lowest possible scalar, which is of course the Higgs boson, and all the other states. But among them, you cannot play too much with the mass splitting. So even this is interesting in the point of view of possible phenomenological studies. So we have actually all the ingredients to address the unitarity of the 331 model. So again, what we did was just to redo the standard analysis. So we considered the 2-to-2 bosonic amplitudes, basically, but now within the context of the 331 model. And this means that now your bosons can be the Z, the W, the Z prime, your YA, the VB, all the neutral Higgses, the pseudoscalar, and all the charged states. This means that the matrix that I showed for the standard model, which was a 7x7, if I remember, or a 6x6, sorry, now will contain block submatrices with electric charge 0, 1, 2, and whatever. So the mass matrix for the scattering amplitude is actually really big. And just to give you an example, of course, the largest block is the neutral one, is the one related to the Q equal to 0. And it is a submatrix of order 30. So it's a 30 times 30 matrix. And it is just one submetric of the whole matrix that you can construct. So at the beginning, our idea was to consider the problem only from the numerical point of view, because we thought that the dimension of this matrix will not allow us to have analytical constraint. In any case, if you want to address the problem analytically or numerically, what you have to do is to consider the eigenvalues of the scattering matrix. And you can take, of course, the S to infinity limit just to be it's easier, of course. And all your eigenvalues, so the maximum of your eigenvalue, of the eigenvalues should be, again, less or equal to 1/2. As I said, at the beginning, we thought that the problem was too hard to be addressed analytically. But in the end, we found that the eigenvalues of these monster matrix are actually in this list. So here you have the lambda E, lambda Ej, and the zeta Ej are the parameter of the potential. And they will come basically in this combination. So lambda E over 8 pi, lambda Ej over 16 pi, and whatever. And these P1 and P2 are actually the roots of these third grade polynomials. So even if the formulas are not so straightforward, we actually were able to find the eigenvalues, the analytical expression for the eigenvalues of the scattering, the 2-to-2 bosonic scattering matrix, and hence these are basically the analytic expression for the unitarity constraint in the 3-to-1 model. Another thing that I want to emphasize is that as one can easily do in the standard model, one can trade this parameter, because we actually give even the analytic expression for the lambdas in terms of the physical masses of the scalar sector. So in principle, but here the calculation is really hard, because one should use this set of equation with at least this set of lambdas. But in principle, it is possible to express the unitarity constraint in terms of physical masses of the scalar sector, exactly in the same way as you do in the standard model. The only difference is that there you have only the Higgs mass, that is the unknown, let's call it unknown parameter, at least when it was studied for the first time. Here, the situation is really more complicated. In the end, one is somehow forced to consider a numerical analysis. So let's come to the last part of the talk. So the boundedness from below of the scalar potential. This will somehow conclude our study on the scalar potential, in a sense that now we are able to set all the theoretical constraints that are needed to select, for example, benchmark points for a phenomenological study. So let's go step by step. The boundedness from below of the scalar potential is actually, as this is very well known, of course, is the analysis of the highest powers of the field. So in a renormalizable quantum field theory, you will have to look at the fourth power of the scalar potential, fourth power in the field, of course. So this is not so easy in multi-Higgs models, and some results, actually many results for the 2HDM, so for the 2 Higgs doublet model, and many results even from the constructive point of view were obtained in the case of N doublet. So here is a a small list of reference where you can find very interesting studies, again, on mostly doublet extension of the standard model. So this is the first time that it is actually, this analysis is considered in a model which has a larger representation, larger than doublets. So to analyze the BFB in the treated models, we consider these we rewrite the fields actually with the help of this chi number representation. So the index I, of course, will run from 1 to 3. And in particular, the fourth grade scalar potential will be given in the expression that is given here, which we can split in a radial part and an angular part. The radial part is, of course, related only to the radial coordinate of each field, whereas the angular part, here the lambda prime and z prime are renamed for the sake of convenience for the future, for the analysis actually. This radial part will be related to this quantity tau ej, which gives actually the angular amount of the scalar potential. So the problem in the boundedness from below is that one should be able to write the potential in terms of the bilinear Ri and Rj, and the BFB will be given by the copositivity of this. Okay, sorry, this Q should be a. It's a typo. I'm sorry. Should be given by the copositivity of the matrix obtained in such way. So in general, for a rank 3 matrix A, here there are no typos. The copositivity constraint for a generic rank 3 matrix are given here. So one is able from the entries of the matrix to say if the parameters, so the parameters of the potential will satisfy the BFB condition, so the copositivity constraint or not. Again, the relevant part of the treated potential here is a kind of repetition, is given by VR plus VA, and I rewrote for the sake of clarity. And the problem is that as you may imagine, the radial part is already suited for the application of the copositivity constraint, so is okay for extracting the BFB condition, whereas the angular part is not directly expressed in terms of the bilinear R1, R2, or in general Ri, Rj. So should be treated properly before applying the BFB condition. And this treatment is actually an angular minimization of the angular, is a minimization of the angular part. So we look for angular minima of the scalar potential, and after we were sit on this angular minima, we were able to express the scalar potential in terms of the bilinears of the field. So,
I apologize, we already are over time, so if you can finish.
So I will just show you there are 3 cases: a simplest one, a next to simplest, and a next to simplest. And in the end, you are able to construct the necessary and sufficient. We were able to construct the necessary and sufficient BFB condition for the scalar potential, and that's it. I'm just arrived. So I will skip the conclusion because you can read, and thanks for your attention.
Okay, thank you very much. A nice talk. Are there any urgent questions or comments? There is one question by Renato.
Yes,
please.
Hello. Very interesting, the bottlenecks from below in a 9 parameter space.
Thanks.
I was wondering though, so you mentioned that the B parameter, the beta parameter for charge quantification takes some finite values. If you actually make it concrete, wouldn't you get even a tougher problem with more parameters?
Sorry, in what sense you make it concrete?
So, for example, substitute by square root of 3 or one of these finite numbers. Would you get more terms?
Okay, as I was saying, there is a problem. It's not a problem actually. In the case of beta q equal of 1 over square root of 3 plus minus, because it's beta squared in the expressions. I can explain in very easily. So two of these of the scalar state of the scalar multiplet will fall into the same representation. Here, as I also put the you can see here. Here you don't have the X charges, which actually are the relevant charges in for this problematic situation or the interesting scenario, let's call it. But the problem is that when beta q is unspecified, so if you consider that is theoretically a generic parameter, each of these representations are different. When beta over q became 1 over square root of 3, two of them will fall in the same representation. And this means that you can construct, for example, more invariants. So the potential is actually larger than this one. So one problem for this point of view is that it is not possible anymore to trade the parameter in the way that we did. And moreover, more invariance means that the BFB analysis is more difficult, because what we were able to prove is that if the potential is given in this form, then we have the correct expression for the trading of the parameters, and the BFB conditions are the one that one can extract as in the way that we did. If the potential for any reason, including the possibility of extra terms or any other things that you can have in mind, is different from that expression, you will not be, the analysis is simply different. Probably it can still be done, even if it's not that clear to me how easy is to arrive to explicit expressions, but at least they cannot be put in the same form as we did. There is actually a way to somehow overcome this problem, but you will have come into phenomenological constraint, because you can imagine to add, let's say, a global U1 symmetry that will protect extra terms in the potential. But then this, if you do not break, as you know, of course, if you do not break this extra U1 symmetry, you will have an Ambu-Goldstone in the spectrum. And in the moment you broke the symmetry, you will not have the same potential, so the analysis will not hold anymore. So in the paper, we actually stressed out the point clearly, because it's really interesting, but it's rather complicated to, at least it was not clear to us if explicit expressions can be done, can be obtained. But yeah, it's true. You can, in one case, have some problem.
Thank you.
Okay, we have to move to the next talk. So thanks, Antonia.
Thanks
again. Thank you.
And, let me stop sharing.
Yeah, please stop sharing.
Just a second. Okay.
Okay. So the next speaker, yeah, please share the screen.
Okay.
Okay. Yeah, excellent. Okay, so the last speaker of today's session is Antonio Gallerati, and we'll talk about supersymmetric theories and graphene. Please start.
Okay, good evening. I am Antonio Gallerati from Politecnico di Torino. First of all, thank you to all of you for this nice opportunity to give this talk about supersymmetry and graphene. So, first of all, this is the outline of our of this presentation. We will have a brief introduction just to say why graphene is important for high energy physics and how to open mass gaps in graphene-like bidimensional materials. And then we will see if it's possible to obtain or to describe from these physical properties of bidimensional materials using a top-down geometrical approach. In particular, we will use holography to obtain the so-called AVZ model. And we will use it to try to make contact between the well-known microscopic formulation and the new geometric macroscopic formulation coming from a gravitational theory. And finally, we will briefly analyze the obtained results and possible future developments and studies. So, first of all, why graphene is important for energy physics? Graphene is a nice framework if one wants to study the behavior of a quantum field in a real curved space-time that is a condensate system, that is the graphene sheet. We have a very nice natural description of the properties of the Dirac charge carriers in terms of pseudoparticles obeying a Dirac equation. There is the possibility to observe a relativistic particle behavior at sublight speed regime that is in the graphene sheet. We have a pseudo-relativistic behavior where the limiting speed is the Fermi velocity rather than the c, the velocity of light. And finally, we can also analyze the curved space configuration. That is, we can directly observe in a laboratory the quantum behavior of a quantum field living in a real solid state system that is curved. There is a curved, possibly curved graphene sheet. Okay, so first of all, some basics properties of a graphene lattice. This is the well-known honeycomb lattice where we have isolated a single hexagonal cell. We can see that the global lattice can be split into two interpenetrating sublattices that here are denoted by red and green spot. And this is the single hexagonal cell that lives in the real space configuration. And then we have the so-called first Brillouin zone that lives in the momentum space that has the same hexagonal form of the graphene hexagonal lattice, but it's rotated by an angle of 90 degrees. And we can, the first Brillouin zone is very important because of the 6 corners of this zone. We can see that the charge carriers have a linear dispersion relation for the velocity. That is, the charge carriers behave as they are massless. That is, they obey a massless Dirac equation. And the 6 points at the corners of this first Brillouin zone are not inequivalent, are not all we can find only 2 inequivalent spots that we decided to label as K and K prime, the so-called 2 valleys of the first Brillouin zone. So, first of all, let us imagine a pure graphene sheet. All atoms are carbon and are carbon atoms, and the sheet is isolated. So this kind of system is very well described by the so-called tight-binded model. That is, we consider very far apart ions in the lattice. This is the Hamiltonian of the system. We can see that the electrons, the charge carriers, can only tunnel to their first neighbor atoms. And in this Hamiltonian, T1 is the hopping amplitude, and C dagger and C are the creation and the annihilation operators. And from this kind of model, we obtain a massless formulation that is robust, since it comes at the level of non-interacting systems and is protected by the presence of parity and time reversal symmetry of the described model. Then, now let us imagine we want to generate mass gaps in a graphene sheet or a more general graphene-like bidimensional material. The idea is that we have to break, in some sense, the symmetries of the pure graphene sheet. That is, we have to break parity symmetry and time reversal symmetry. And this kind of symmetries can be broken and described using the so-called Haldane model. The physical situation can be, for example, local magnetic fields that spoil the time reversal symmetries, the time reversal symmetry of the system, or, for example, on-site staggered potential that spoil the parity symmetry of the system. This can happen, for example, when you have a lattice with different kind of atoms, for example, boron nitride lattice, or also pure graphene that is the deposit that we can decide to deposit on some kind of substrate that induce local on-site potential, spoiling the parity symmetries of the A, B, and B sides of the hexagonal lattice. So this is the Hamiltonian of the microscopic model describing this kind of physical situation, the so-called Haldane model. We can see that apart from the term H1 that was the type in the previous model, we have these new terms. The first term is the so-called Haldane contribution that spoils the time reversal symmetry of the theory, introducing second neighbor open terms that are modulated by this phase factor whose sign depends on the chirality of the electron path. There is, if the second neighbor hopping is traveled clockwise or anti-clockwise, and this clearly spoils the time reversal symmetry of the system. And then we have this on-site potential plus or minus m, where the plus refers to the A site and the minus to the B site of the honeycomb lattice, or vice versa. And this clearly breaks the parity symmetries of the parity symmetry of the model, since it spoils sublattices equivalence. From this kind of model, it's possible to easily read the fermion masses at the K and K prime valleys, that is at the Dirac points, where where now the Fermi are not massless, since we have broken the symmetries of the system. And these are the true fermion masses that we can see that they are different unless the Haldane contributions is 0. So in principle, we can generate mass gaps. We can describe it with the well-known microscopic models with the correspondent fermion masses in equivalent values. Now, the question is it possible to describe, to obtain, to predict some of the properties using a top-down approach? Well, in principle, it should be possible using the so-called holographic correspondence. There is a particular conjecture that says that if we have a d+1 dimensional gravitational theory defined into an anti-de Sitter spacetime, is it possible to infer some of the properties of a conformal quantum field theory defined at the boundary of this gravitational model that lives in the bulk? What we want to say in particular is that there is a one-to-one corresponder between the quantum operators of the quantum field theory defined at the boundary and the fields of the bulk gravitational theory. And in particular, boundary condition for these gravity fields living in the d+1 gravitational theory in the bulk can be used to act as sources for operators of the quantum field theory defined at the boundary, that is at the radial infinity, if you want. So with this idea in mind, our purpose is to write some kind of, clearly the idea is that the gravitational theory should be some kind of four-dimensional gravitational theory defined in the bulk, and the three-dimensional boundary, or better, the 1 + 2 dimensional boundary should be our 1 + 2 dimensional bidimensional, space bidimensional plus 1 dimension graphene lattice. Okay, so we start writing a gravitational model in 4 dimensions, and then try to write the correspondent effective theory in the 3-dimensional boundary. And this effective theory defined at the boundary should feature, we hope that it presents a spin 1/2 fermion that lives in this curved boundary background. And then we clearly have to check if this new generated spin 1/2 fermion living on the boundary can be, in some sense, identified with the Dirac charge carriers on the graphene-like material. So, more in detail, with the procedure. We start from a gravitational supersymmetric supergravity theory defined into an anti-de Sitter space with a maximally supersymmetric vacuum. And then we consider fluctuations living on this background. Then we have to write the algebra for these fields. So we have to write the Maurer-Cartan equation, and then we try to study the form of the Maurer-Cartan equation at the boundary that is located at radial infinity. Then once we have considered this boundary limit, we have to define the new correct form for boundary fields, connections, and field lines living on the ultraviolet boundary that is in the 3-dimensional model. And finally, we can see that the resulting 3-dimensional model describes a so-called generalized AVZ model that has a particular local Nye-Yawile symmetry. There is a particular local scale invariance symmetry of the theory. Now, what is a generalized AVZ model? So the name AVZ comes from the creators of this model, that is Alvarez, Valenzuela, Zanelli. And it is an effective theory in 3 dimensions featuring a spin 1/2 fermion that we call chi. It's defined, and this is okay because we want to describe spin 1/2 fermion for graphene. It is defined on a curved geometry so that we can have some kind of general relativistic analog phenomenon, and this is good. This system is particular because it exhibits an unconventional form of supersymmetry, and then we will see what unconventional means for us. And then we have fermion fields that obey Dirac equation, so they may be used to describe the pi electron, that is the charge carriers in graphene bidimensional sheet, and in the 2 inequivalent valleys k and k prime. So this model can be holographically realized as the boundary theory of a supergravity gravitational theory, classical gravity theory defined into the anti-de Sitter spacetime. We obtain an explicit form for a Dirac equation for our charge carriers, and most important, the fermion masses, the physical quantities of the real system, the real condensate system, can be expressed in terms of geometrical quantities. For example, the torsion of the new considered spacetime, 3-dimensional spacetime. Okay. So, what does unconventional means? The idea is that we use a particular ansatz for the fermionic gauge fields, that is the gravitini, and we can see that these fermionic gauge fields for our 4-dimensional theory can be written in terms of the spin 1/2 fields chi, defining fermions in the 3-dimensional boundary. Then we need to write the explicit form of the algebra, and this can be done in terms of a connection that we call A, that in turn can be explicitly written as a combination of fields times generators, and this connection must satisfy the Maurer-Cartan equation. Then this construction, as we already said, leads to the description of a shared fermion satisfying the Dirac equation, and this new fermion can be used to describe the electronic properties of graphene-like 2D materials. Then main results that we obtained using this geometrical top-down approach. First of all, we started from an extended supergravity model. This model has an ADS4 vacuum that has a particular orthogonal symplectic group of symmetry. And then we related this four-dimensional model to a three-dimensional AZ model that features a particular group of symmetry that is given by this product of these two sectors, plus and minus sectors, depending on these P and Q integers parameters. So that the sum P plus Q must give N. That is the number of supersymmetries of the supergravity model defined in the bulk. So if now we restrict to the particular P equal Q case, first of all, parity now is a discrete symmetry of our theory. Parity symmetry, parity for us is some kind of reflection with respect to an axis that is tangent to the three-dimensional systems. If P equal Q parity is a symmetry of the whole theory, the boundary, that is the three-dimensional model, can be reached performing the limit R that goes to infinity. And then we can also write an explicit parameterization, explicit expression for the four-dimensional field bind that is uppercase E. And we can see that this expansion at the boundary for R that goes to infinity can be written in terms of the three-dimensional, that is the three-dimensional field bind, that is this lowercase e. So that at the boundary, we can expand the four-dimensional field bind in terms of the three-dimensional field bind. And then we will use these results. And finally, very important, these plus and minus sectors of the theory can be naturally put in relation with the two inequivalent valleys of the graphene-like bidimensional materials that we call the K and K prime. So there is a correspondence between plus and minus and K prime. So the torsion, that is a pure geometrical quantity of our three-dimensional system, has this explicit expression, and we can see that it depends on this tau plus minus parameters. We can see the grading plus minus, that is we refer to the plus or the minus sector of our symmetry group. And this in this tau plus minus can be written in terms of geometrical quantities. This parameter tau that we are going to analyze, and this ratio f over L, where this f was the function that was that acts as a proportionality factor between the four-dimensional field bind and the three-dimensional field, and it is another geometric quantity. So these tau plus minus parameters are written in terms of this f, these are geometrical quantities, and L, that is the anti-de Sitter radius of our system. So everything is written in terms of quantities referred to geometry of the system. Then we have an explicit form for the Dirac equation of our spin 1/2 fermion living in the three-dimensional boundary that we call chi. This is the explicit form of the Dirac equation, and we can see that from this equation we can read the masses of the chi fermions, and these masses proportional to these parameters tau plus minus, that is the masses written in terms of geometric quantities. And here we have written tau plus minus in terms of this expression. Finally, the spin connection living in the boundary, we can choose the form of the spin connection living on the boundary, and this choice can be labeled by this parameter lambda. This is a real number that in turn can be used to rewrite an explicit expression for this tau parameter. So that the tau parameter depends on this lambda, on the function f, and on the anti-de Sitter radius. There is geometric properties of the obtained model. And this is now the explicit expression for the tau plus minus that in turn give us the masses of this spin 1/2 fermion living on the boundary of the gravitational, on the three-dimensional boundary of the gravitational theory. Clearly, now the idea is that to try to find a relation between the spin 1/2 fermion and the real spin 1/2 charge carrier of the real condensate system, that is the graphene or the graphene-like bidimensional material. So that we want to make contact with the previous well-known microscopic formulation, that is the Haldane model that we presented at the beginning of this talk. So the idea is that the electron charge carrier wave function for an electron living on the graphene sheet that we call psi can be written in terms of the boundary field chi, in this simple form, where this factor is used to obtain the correct normalization and the correct dimension for to the -1 is the inverse of a simple matrix that is used to make contact from the convention that we used in our model to write the gamma matrices and the standard convention of the gamma matrices of the Haldane model. Then if we use this expression for the direct charge carriers, we find, first of all, that the fermion masses, as we already said, depend on geometric quantity of the model. This is the torsion of the three-dimensional boundary space-time. We find a very, very nice top-down approach that tells us that the effective three-dimensional theory of the boundary comes from a well-defined pure supergravity theory defined in the book. That is, we start from a classic gravitational quantum field theory in the bulk, and we can predict physical properties of a three-dimensional system living at the boundary. The fermions of this theory may describe the properties of the electrons at the Dirac points of a graphene sheet, of a graphene-like bidimensional material. And in particular, we can find a correspondence between the Semenov and Haldane time mass contribution. This is the form of the masses for our fermion fields living on the boundary of our model. And these are the masses of the electrons at the K and K prime valleys of a graphene-like sheet. And we can see that there is a correspondence. We can put in relation the Semenov parameter with the tau, the geometric tau parameter. And then we can also identify the Haldane contribution with the ratio of the ratio F over L, that is geometric quantities. The F relates the four-dimensional with the three-dimensional field line, and L is the anti-de Sitter radius. So, summarizing the conclusion, we have seen how it is possible to use this extension of an unconventional model of supersymmetry to obtain and describe electronic properties of graphene systems in the two inequivalent valleys K and K prime. And then we have used it to describe a particular situation, physical situation, for example, local magnetic fluxes or on-site potential that spoil the symmetries of the theory and open mass gaps. And this is possible, and we can describe this physical situation using our gravitational geometrical model. And we obtained a well-established top-down approach so that our effective three-dimensional model originates from a gravitational theory defined in the bulk. And among the possible future developments, there is the possibility to identify the Haldane parameters with the geometrical quantities. The identification that we've seen between Haldane parameters and geometrical quantities suggests a possible relation between the ratio F over L and the physical quantity that is the Berry phase parameter of the model in case of time reversal breaking, in case of breaking time reversal symmetry of the model. And finally, we can embed, since we find an embedding of this and extended the gravitational theory in a well-defined ground, We can also perform further of holographic analysis to extract and predict new physical quantities for particular bidimensional materials. So they can extract condensed matters system properties from a pure gravitational theory. Thank you.
Okay, thank you very much for a nice talk. Any questions? Comments? Okay, I don't see any, so thanks, speaker, again. Okay, so there is a question, actually. Pablo, Pais?
Yes. Can you hear me? Yes?
Yeah,
yes.
Yes.
Mm-hmm. Please go ahead.
Thank you for the talk. Very nice talk.
Thank you very much.
I would like to know, in your case, the belly breaking of, there is a symmetry breaking between K and K prime, right?
Yes.
It is, in your case, it is parity symmetry breaking, or which symmetry?
We have in the microscopic formulation, we have broken both time reversal symmetries, time reversal symmetry with this Haldane contribution, where the second neighbor hopping terms depend on the chirality of the electron path, and this breaks time reversal symmetry of the model.
Okay.
And where we have an on-site staggered on-site potential, and this clearly breaks parity symmetry of the system. So in the microscopic formulation, we have broken time reversal symmetry and parity symmetry of the theory. For example, we can consider a boron nitride lattice, or also a graphene sheet that it deposit on a substrate that induce local on-site potential, so that it breaks parity symmetry. And also with local magnetic fluxes, we can also break time reversal symmetry of the system. The idea is that with the geometrical description, we can take into account these two possible physical situations. That is, breaking parity, breaking time reversal symmetry, or breaking both of them.
Both of them. Okay. So, and in your, this is translated in the ABC description in this two kind of flavor, let's say.
Yes, we have some kind of grading with respect to these two sectors.
Okay. Yes, sure.
We have some kind of grading, and the plus and the minus are put in relation with the K and K prime values in some sense.
Okay.
And then, depending on the geometrical parameter of the theory, we can have a Semenov contribution. That is, we have broken parity of the symmetry, or we can have a Haldane contribution. That is, we have broken time reversal symmetry of the system, or both of them.
Or both. Okay. Yes. Yes. Thank you.
Thank you.
Okay. Thank you very much.
Thank you.
No more questions. If not, thanks, speaker, again. And this concludes today's session. Thanks all the speakers, and I will see you tomorrow.